Good morning, Deepak sir.
Yeah, good morning, sir. Let me rejoin actually. I'm facing some problem here.
No issue, sir. Yes. So I welcome to all the participants here in the fifth day of the FPP of Deep Learning, which is organized by the ENICT Academy, MNIT Jaipur. So now is the first day of first session of the fifth day. So now this session that will be taken by Dr. Deepak Ranjan Nayak sir. He has already taken two sessions, the Bayes decision theory and the linear discriminant function. So now here in this session, we will take on the topic segmentation model and zero shot learning and segmentation. So now sir is now with us. So Dr. Deepak sir, I welcome you again back here in this FDP of deep learning.
Yeah, thank you. Thank you. Okay, so am I audible?
Yes, sir, perfectly.
Okay, thank you. This, um, Okay, so is my screen visible?
Yes, sir, visible, sir.
Okay,
And your
thank you.
voice is also yes.
Yes, yes. Thank you. Yeah, so good morning, participants. So in this session, actually, we'll be talking about deep learning based, deep learning based state-of-the-art image segmentation models, especially, and we'll also talk about some of the challenges and future prospects in this direction of research. Right. So I hope you all are enjoying this course, deep learning. Most probably, you have learned convolutional neural network and several, you can say, variants of convolutional neural network. So which all are important to design this image segmentation models, right? So we'll see one by one. I mean, the different kind of image segmentation models that has been designed over the years from 2015 to 2022, 2024, right? So in this particular lecture, I'll be touching upon, what do you mean by image segmentation? What are the different types of image segmentations we have? And why do we are interested in solving the segmentation models, right? Or especially segmentation problem, right? With the help of learning-based algorithms, and especially convolutional neural network and vision transformer-based models. And what are the limitations working with convolutional neural network models, and how to improve, or how to address the challenges? Introduction to attention mechanisms, the approaches that has been developed for image segmentation problems, which incorporates attention mechanism. Probably attention, there is a dedicated, I think, session for attention mechanisms where you get to learn more about attention mechanisms. I'll just give you an overview that why do we need attention mechanisms, how it performs, or how it helps in improving the performance of the convolutional neural network models, as well as vision transformer models, right? Vision transformer is again one of the, I think, session that has been dedicatedly designed where maybe some other speaker will discuss about the transformer. But here also I will talk about some of the image segmentation models which are vision transformer based. Yeah, there are some case studies which we have been working with since last 1-2 years, right? We've been trying to solve some of these segmentation problems, especially medical image segmentation problems, right? Also, what type of algorithm we have designed, and what are the challenges, and what are the future scope, right, in this direction of research. Here is a glimpse of work which we solve at our lab, VAPR lab, Vision Analytics and PR lab, Pattern Recognition lab at MNIT. You can see there are a couple of even image segmentation tasks, right? Like the first one is image segmentation task, which is a fundus image analysis. Like I'll show you also, like what do you mean by diabetic retinopathy, and how to segment different lesions of the diabetic retinopathy disease, which is especially eye disease, right? Okay, so let us directly jump to what do you mean by image segmentation, and how the output looks like, and how it is different from the other popular tasks like classification, right? Objects, basically object detection, and there are different types of even image segmentation tasks we have, right? I will discuss it in detail. So segmentation is nothing but partitioning an image. Given an image, your task is to just partition the image, right, into multiple segments and objects. If you can see, there are a couple of examples and also the corresponding outputs, right, after segmentation is given. Here you can just consider, let's say, this one, right? So if you can consider this image, right? So you can see, so what we're trying to do here is we're trying to just segment, or we're trying to partition the image into different segments or objects. So here especially, we are trying to partition the image into two particular types of segments. One is like cycle or bicycle, and one is a person. So the next example you can see over here. So we are just trying to highlight here, right, some of the vehicles. At the same time, you want to partition into different objects. So here it is vehicles, and there's a person over here, right? We'll see how we can solve this problem, and how we can simulate this kind of problem so that we can solve with the help of convolutional neural network, right? But the kind of convolutional neural network which we have seen till now is best for solving classification tasks. Cannot be directly used to solve image segmentation tasks. So we'll see what are the changes we have to make in the convolutional neural network architecture so that we can solve image segmentation problem. So one thing that is clear, what it is obvious here, that is, in case of image segmentation, the input is an image, the output is also an image, right? So this is actually the major difference, right, between image classification and segmentation, where in case of image classification, given an image, your task is to just to provide a label, right? And your model in general gives us a probability score, and based on the probability score, you are used to define a label for a particular image, right? But here, in case of image segmentation, if you look at here, the output is nothing but an image itself, right? But this image is nothing but a segmented image. So we'll see how we can formulate, right, this image segmentation problem as a classification problem, but it's a pixel level classification problem. So before that, let us first have a discussion, right, on the difference between classification, image segmentation, as well as object detection, right? So you'll find its applications, right? Starting from medical image analysis, where you need to sometimes identify the tumor boundaries and all. Sometimes if you want to measure the tissue volumes of any lesion area, that is also possible with the help of image segmentation. Autonomous vehicle, video surveillance, scene understanding are a couple of such application area where you will find, right, the usage of image segmentation, right? And there is an interesting article. If you want to read, you can read. You will get a lot of information from this paper, right? Image segmentation using deep learning, a survey, which is published in IEEE PALM. It's one of the topmost journal in the field of computer vision. Yeah. So yeah, if you want to differentiate, right? Just now we have discussed about how this classification is different from image segmentation. So in case of classification, what we focus is what is in the image, right? That's it. And we want to just assign a label. That's what we discussed, right? So classification with localization, you can see this kind of, examples. This is best suited for classification with localization. So you need to focus here what is in the image, at the same time where it is, right? In case of object detection, you can see over here. So we are focusing on what are the objects, right, that are present in this image and where are they. That means you have to provide a bounding box, right, for each of the objects. But in case of semantic segmentation, our task is to actually classify all the pixels, and you need to define that whether each pixel, each pixel belongs to which objects, right? I'll define it in more detail. And there is something called an instance segmentation. I will also discuss how the semantic segmentation is different from this instance segmentation. I have a couple of examples to show you. Let us first focus on the semantic segmentation, right? So the semantic segmentation, let's say given this image, you want to predict this kind of image. So you can just define it as a task of grouping similar type of pixels in the image, right? So what does it mean? Now you see, let's say in this particular image, right, I want to focus on only two objects. I want to partition this image, right, into two objects especially. One is bicycle and one is person. You can see over here. So I've just given, right, I've just highlighted two objects over here. One is bicycle and one is person. And and rest other pixels can be easily classified into background. So this kind of problem statement can be casted as a pixel level classification problem. So what do you mean by pixel level classification here? For every pixel in the input image, right? For every pixel, you have to assign a label in the output image. And what could be the possible levels? There are three levels. Either that pixel will belong to person category, or belong to bicycle category, or the background category. So always these are actually known as number of classes. Let's say, for example, C, and always the final number of classes will be C plus 1, including the background. Would you follow? So this is very, very important to understand, because based on this concept only, we are going to design the convolutional neural network. For every pixel, as I mentioned, so you need to classify every pixels in the image, into either of these three categories: person, bicycle, and background. So now the segmentation problem has been formulated into a pixel level classification problem. The traditional image classification problem is nothing but an image level classification problem, where for every image you need to give a single level. But here for every pixel you are assigning a level. And what are the levels? It all depends upon the number of objects you want to highlight or you want to segment, right? But in case of classification, you might have remembered that input is an image. Of course, let's say this is an image, and output is just a level. And you want to just find out the relationship between x and y, that is f of x. And maybe if you are using convolutional neural network, or let's say traditional neural network, right? So you can easily predict this f from this. But the kind of output you are dealing with is just a value, just a single level, right? Maybe in this category, you can just give single level here. Let's say, let's say, for example, 0 or 1, like this, right? However, and we're only talking about here supervised learning scenario. Supervised learning scenario, where we need both x and y. In case of semantic segmentation, as I mentioned, it can also be casted as a pixel level classification problem. So how the y will look like, right? So y is not a single value here. Rather, y is the whole ground truth here, right? So that means there must be pixel level annotations given to us to design, right, a model here or supervised model. So that means x is an image, y is also an image over here. Instead of a single value, right? Here in case of semantic segmentation, because you want to assign a semantic category to each of the pixels, that's why the name is actually so-called semantic segmentation here. So y is also an image, right? So that means collecting or annotating, right, these kind of images is a costly process. What does it mean? So assigning or annotation or labeling of image, in case of image classification, traditional image classification is rather easy. The output levels I'm talking about. But in case of segmentation, the annotation is quite intensive. You can see over here, because we need pixel level annotations to get Y, right? And this is very, very important in case of supervised setting. We must have ground truth. We must have output levels. But getting the output levels is really difficult in case of segmentation algorithms. In case of, especially, while you are solving a segmentation problem using supervised learning algorithms. But still, we are interested in solving this kind of problems, right? Yes, there are a couple of developments using the recent literatures that people are interested in semi-supervised learning algorithms, unsupervised learning algorithms as well, with the help of convolutional neural network. The traditional, okay, but before I get into right, the algorithms, or you can say the convolutional neural network models, which can solve this kind of problem, let us also discuss about the types of segmentation problems we have. So semantic segmentation, just now we have discussed, right? And there is something called the instance segmentation. I hope you can just see these two images and try to find out the difference between semantic segmentation and instance segmentation, right? So instance segmentation differentiates between different objects of the same class. You can see in case of semantic segmentation, we have just labeled this one and this one as a person, but here you can also, if you want, you can also make a differentiation between the same classes of these images. Like here, right? Previously, we have just highlighted these are like vehicles, but in case of instance segmentation, you can just highlight it as a car, it is a truck, like that. And panoptic segmentation is nothing but it's just both semantic. When you combine this both semantic and instance segmentation, then it becomes panoptic segmentation, which is really challenging compared to this two. Right. So the goal of this particular session here is to focus only on the semantic segmentation, and if you want, you can also explore this instance segmentation and panoptic segmentation. Right. Before I discuss the kind of architecture that has been developed using convolutional neural network to solve segmentation problem, let us also see what are the traditional segmentation methods which you have seen in image processing. So thresholding is one of the simplest approach for solving segmentation problem. What do you mean by thresholding, right? So given an image, you have to set a threshold based on the intensity values or the color values. And if every pixel is greater than that threshold value, then you can just make it 1 or test values will be 0, like that. It's difficult, right? To solve the segmentation problems, right? In the practical scenario, especially, you may not get accurate, results using thresholding, but yes, this is the simplest one to solve the segmentation problem. And there are also a couple of algorithms like Watersed, Graph-QuAD algorithms, region growing algorithms, and the most popular one is a k-means clustering approach, which you might have learned in machine learning, right, for solving clustering problems. But this kind of segmentation problem can be also casted as a clustering problem, where your task is to group the similar types of pixels. You need to first tell what will be the number, what will be the value of k, right? And this is also one of the limitations of k-means clustering algorithm, right? Where you need to first define that how many clusters are there. Let's say you have decided k value is 3, and then you know how to solve these problems, right? You need to decide the centroid for the 3 clusters, and then you have to assign every pixel to the closest centroid, like that. All these approaches are actually unsupervised in nature. What does it mean? So they don't require actually the ground truth images. So then why we're interested in solving the segmentation problem with the help of learning-based approaches like convolutional neural network and all. So of course, as I mentioned, that the performance, right, of these algorithms, although they don't require the ground truth images, the performance, right, doesn't meet the requirement of the real-time scenarios, right? And if you go through the literature, you will find that although these deep learning models, right, like convolutional neural network and Bayesian transformer models, demands ground truth images, which is obviously quite annotation intensive, but still it is giving remarkable performance, right? Or sometimes even human level, it is giving human level performance, right? While solving this segmentation task. So we'll see why it is giving and what are the algorithms, right, that has been developed over the years. So I don't want to, even discuss the advantages of the deep learning algorithms. Probably some of the other speakers have discussed, right, why there is a need of deep learning algorithms, right? So I will only let you know that yes, there are two algorithms, right, especially two models, you can say, or two architectures of deep learning, which are very, very popular in solving image segmentation tasks, or even classification tasks, you can call it as, right? I mean, like convolutional neural network and Bayesian transformers. So when we talk about solving some image and video centric problems, right? So solving some image and video centric problems, so we usually use convolutional neural network and Bayesian transformer, right? So why? Because okay, I have also I think slides, right? Although there are certain advantages of deep learning architectures, right, for giving us better results, but it also demands huge amount of data for effective learning, and it is computationally intensive. You might have seen that how many, parameters are required by the convolutional neural network compared to the traditional neural network or traditional even machine learning algorithms, right? So the parameters are always in terms of millions. Sometimes it is beyond 100 million, like that, right? So so then why we're not interested in traditional neural network? Why we're interested in convolutional neural network or Bayesian transformer kind of models for dealing with image and video centric problems, right? So yes, there are a couple of advantages of using convolutional neural network over traditional neural network. I don't know whether this part has been covered or not. Why we are not, or what are the disadvantages, or you can say, of using traditional neural network for processing images and videos. So can you tell me what are the possible reasons? I mean, why we are not interested in analyzing the images through traditional neural network? So let's say this is a traditional neural network where you can see there are input layers, output layers, right? And there are three hidden layers I have chosen over here. And let's say, for example, I'm dealing with images, right? And this is an image having size 256 cross 256. I'm just considering a grayscale image over here. I don't have channels like RGB channels over here. For simplicity, I'm taking this one. And I want to process this image with the help of this network. So is it possible to process? You can write your answers in the chat box. Is it possible to process this image with the help of traditional neural network? So I could see the answer is no, right? Yes, any other answers? Two answers I could see. My question is it possible to process? Yes or no? So then we will see the disadvantages, right? The question is it possible? If possible, then how to process the image with the help of the traditional neural network? If the input is given in the form of traditional means not CNN, it's just neural network having layers or dense layers together like this. There is no convolution over here. See some of the yes, they are saying that yes, it can be processed. So then how to do this? So you need to first unroll this matrix. Yes, yes, yes. Yes, we will convert to one-dimensional vector. Absolutely. You are correct. So that means I have to first convert this image into a one-dimensional vector. And this vector is having dimension 256 into 256. Are you all agreeing? Because we have this many number of pixels. Image consists of number of pixels arranged in a either two-dimensional or three-dimensional matrix or grid. And for every pixel, please write some color values, intensity values, lies from 0 to 255, right? And sometimes if you want to normalize, you can also make it from 0 to 1. So 0 stands for black, 255 stands for white, right? What I'm talking about. So similarly, in case of RGBs, we'll be having 3 channels, right? So every channel, if you just combine the colors, so you will have different colors. It's like an 8-bit image I'm talking about. 8-bit image having 256 colors. Color images are in general 24-bit images. Right? So you'll be having 2 to the power 24 number of colors you can produce. Fine. So what is the steps to be followed here to process the image with the help of this traditional neural network? So you need to first convert this image, which is nothing but a matrix, when you will store it in the computer, right? In case of this image, it is a two-dimensional matrix. You need to convert this two-dimensional matrix into a one-dimensional vector, and the dimensions will be 2 to the power 8 into 2 to the power 8, probably 2 to the power 16. This many number of neurons, right, you require in the input layer. Fine. So then, yes, if you want, you can process like this. And if you go through the literature, you will also find the success stories of this, right? So people have also processed the digit images, especially, I don't know how many of you heard about something called as a MNIST dataset, which contains, right? MNIST dataset, right? Which is nothing but a digit, you can say dataset with, numeric dataset. Yes, okay, fine. So where the images are like having size 28 cross 28. So probably if you just unroll this matrix into a vector, you will having 784 dimensional feature vector. Or you can say, 784 dimensional vector, input vector. Right? Especially we used to process, process the features in the input layers with the help of different hidden layers, right? But here we are considering like every pixel is a feature, right? But what are the problems? Can you tell me what are the problems you will face while processing the images, right, in the form of the vectors with the help of traditional neural network? What could be the possible reasons? I mean, why we are not interested in this? You can write your answers in the chat box. Are you losing some information by doing this? Are you losing some information by converting a two-dimensional image into a one-dimensional vector? In image, what you know that spatial informations are very, very important, right? I mean, especially the pixel relationships. So while converting this two-dimensional matrix into one-dimensional vector, so you will definitely lose the spatial information. So the correlationship among the pixels. So that you are going to lose, right? So one of the important, you can say the point to be noted here, that yes, you will lose the spatial information. So at the same time, the number of parameters are going to be very, very high. Why? Because the dimension of the feature vector is here 256 into 256. That means it is 2 to the power 16. So there are 2 to the power 16 number of neurons in the input layer. And let's say, for example, I'm having only 100 neurons in the first hidden layer. So the first neuron, because every neuron is connected to every other neurons in the preceding layer, so every neuron will be having 2 to the power 16 number of connections, right? Because every neuron is connected to every other neurons. So that many number of weights will be there. So if you consider 100 neurons over here, so then it will be total 100 into 2 to the power 16 number of weights only in the first layer. Could you follow the number of parameters required? Although we know that convolutional neural network takes a lot of parameters compared to traditional neural network, but if you want to process actually the images with the help of traditional neural network, the number of parameters even go beyond, right, 100 million and sometimes even beyond that, which is much higher than the convolutional neural network. These are the two reasons. Yes, there are also, of course, other reasons, but these are the two major reasons why we are not interested in using the traditional neural network to process images, right, and videos for solving any problem, whether it is segmentation, whether it is classification, right? So how do convolutional neural network handle these issues? Yes, we all know that no need to convert these images into the vectors. You can directly apply the filters, right? You can directly apply the convolution operations with the help of a filter over the image. And at the same time, those parameter sharing is one of the important concept, right, which helps in reducing the parameters. Parameter sharing. What does it mean? So you are, in case of convolutional neural network, let me directly jump to it. Yeah, this is how actually a traditional sequential convolutional neural network looks like. So probably some other speakers have already discussed about convolutional neural network, its advantages, its layers, how it works, right? So I don't want to discuss much about it because it's already been covered. But what I want to highlight over here is this is how actually the convolutional neural network looks like. I mean, the traditional, you can say, sequential convolutional neural network looks like, where you can see a couple of hidden layers, but these hidden layers looks very different from the hidden layers which you've seen earlier, right? So here you will find something called as convolutional layer, something called as ReLU or activation layer. Here, of course, some of the variants of the ReLU as well, right? And why ReLU, why not Sigma? I think these parts have already been covered. There is something called as pooling layer, right? Also known as downsampling layers. And what is most important here in convolutional neural network is this layer, the convolutional layer. And the concept of convolution has been directly brought from the signal processing concept. And also, why convolution, why not other operations? So if you go through the literature, we'll find there are some biological inspirations why convolution has been used, right? Why not other operations, and how convolution is helping in extracting the important information from the images, and how it enjoys different properties like localization, right? And translation and invariance or shift invariance kind of properties, which are very, very important, right? And you know how to apply this convolution operation over the image or over different set of feature maps, right? So there'll be set of filters given to us. So how to apply this? Let's say, for example, there are different filters. I'm just taking one example that if you want to apply a filter over this image, so you need to just place the filter over each pixel, the image, and then you need to just slide this filter over all the pixels of the image. Then you will get one output over here. Fine. So the same filter is used at every pixel positions, right? So that means, and these weights, the coefficients of these filters are known as weights over here. And there's a bias, of course, which is related to or associated with one filter, right? So this is what is actually parameter sharing, where you are applying the same filter over all the positions, right? And that's why actually it reduces the number of parameters. And you can see here that let's say this is one output neuron in the hidden layer, and it is connected to a small region in the input image. The small region in the input image. While in the previous case, we have seen that every neuron in the hidden layer is connected to every other neurons. That is why the number of parameters are more. And that is how CNN tries to reduce the number of parameters, right? You can see over here, this is one of the neuron, hidden neuron, which is connected to only a small region of the image, not on all the pixels, right? So that is how actually it reduces the number of parameters. And this parameter sharing is also one of the important concepts over here to understand. So if you apply one particular filter, you will get a single feature map over here. So similarly, if you apply, right, D number of, let's say, filters, so you will just have D number of feature maps. And if you just stack them together, it will just look like a feature volume or feature map here. And that's what you know already, right? So if you just go through the literature of convolutional neural network, you will find the early convolutional neural network architectures usually contains, right, fully connected layers or dense layers at the end. And now people are not using many fully connected or dense layers. Why? Because this fully connected layer contains numerous learnable parameters, right? You might have heard about something called as AlexNet. In AlexNet usually demands 60 million parameters, right? And out of the 60 million parameters, more than 50 million parameters are because of the 3 dense layers they've used at the end. They have only 8 layers. AlexNet is an 8-layer architecture, right? It is actually having more number of layers. When I say 8-layer architecture, means there are 8 layers which contains the parameters. Not all the layers contain parameters. Layer doesn't have any parameters. It's just a downsampling layer, right? But if you want to perform pooling with the help of convolution, that can take parameters, right? Pooling can be also done with the help of convolution by taking the stride value as 2, right? But if you're just choosing max pooling, like average pooling and several other types of pooling operations, right, which doesn't have any parameters. So usually we use max pooling, then average pooling, and there are also several other types of pooling, like stochastic pooling and all, right? So those do not require any parameters, fine. So as I mentioned that, yes, the last 3 layers in the AlexNet takes more than 50 million parameters. So then later on people thought of why to use those kind of, dense layers at the end. So why not to replace those layers with the help of some convolutional layers and all, right? So you need to be very, very careful while inserting some fully connected layer or dense layer at the end, because it actually, leads to a lot of learnable parameters. Yeah, so I guess there is one more question over here, that why do we, repeat over here? I mean, why do we repeat those kind of operations like convolution, ReLU pooling several times over here? So what are the benefits we get, right, if you repeat this kind of operations? So the goal is to actually extract or learn, right? And you can say, what I'm saying actually learning of the features, not extraction of the features. So extraction of the features is like, it is like a fixed approach where that yes, only these kind of features can be extracted from the image. But why I'm saying it's a learning of features instead of extraction of the features, because the kind of features which you're extracting can also be updated by looking at the output, right? So that is the beauty of this convolutional neural network, that what kind of features you're extracting initially, right, with the help of these filters, you can also easily update those features, right, by looking at the output or in response with the output. And every hidden layer increases the complexity of the learned features. I'll also show you that how these kind of layers help us in learning different kind of features. Like the initial layers especially learn generic features, right, which are like edges, blobs, color features, and which are important. These are like generic features, right? So if you apply any model over any data set, so these kind of features will be extracted, right? So these are like the initial layers will help us in learning those kind of features. And when you go down the layers, so you will find that the later layers especially are nothing but very specific features. The later layers used to learn specific features which are data set dependent, right? Of course, data dependent. If you just modify the data, so obviously the features, right, which you are getting from the last layers or especially the final layers are more specific, right, or specialized features, you can say, right? Yeah. So here is just the evolution of this convolutional neural architecture, which has been developed initially for classification and some other kinds of tasks. Right? It all started from 1998. If you go through the literature, you'll find the concept of CNN is not new. It can be tracked back to even 1980s, but the very first architecture that was published in 1998, and there's a huge gap from 1998 to 2012. Right? There was no development in the field of convolutional neural network because of certain reasons. You all know that yes, convolutional neural network takes a lot of parameters and it takes even a longer time of training. So that's why people were not using. And even at that time, there were no such GPU kind of systems available. Even no systems available to store the data and like that, right? So then suddenly in 2012, AlexNet came into the picture by Professor Hinton and his group. And it was just the result of, winner of one of the challenge known as ILSPRC, which is Image Large Scale Virtual Recognition Challenge, right? So it all started in 2010, and this kind of architecture was applied on something called as ImageNet, which is sometimes known as ImageNet Challenge, which is one of the data set why we have actually, right, these many models, right? So this is one of the largest data set at that time, which was released, and for 2010 and 11, the winners are like shallow architecture based winners, but then suddenly in 2012, AlexNet, when AlexNet was proposed by Professor Hinton. So then people were surprised by the results that AlexNet has achieved for that year, and they have also become the winner for that year. And we all know that Hinton has also recently awarded Nobel Prize because of its huge contributions in the field of neural network. He also developed back propagation learning algorithm followed by other algorithms like autoencoders and all, AlexNet, CapsuleNet. So a lot of ideas he has also proposed, right? Including this architecture, AlexNet, which is the most popular architecture. And then over the years, you will find that people have developed several types of architecture, CNN architecture. So why I'm discussing, why I'm just giving you an overview, because this kind of architecture can also be integrated right into a segmentation model, right, to solve a segmentation problem. Right, that's what I'm discussing. So I'm not going into the details of this, right, because I think most of the architectures have already been covered, right. I just want to highlight that what are the architectures which are very, very popular, like the winners. You can say these are like the winners of 2014, 16, 17, like that. So I mean, if you just but VGGNet is not the winner of for the year 2014. It's a runners-up actually, but still it is very, very popular because of its uniform architecture, right. So in VGG, actually, the authors especially mentioned that no need to use for different kinds of filters, especially different filter sizes like 11 cross 11, 7 cross 7, 9 cross 9 filters that has been used in AlexNet. So in BGG, just they propose to use only 3 cross 3 filter to achieve, right, everything whatever you can achieve using 11 cross 11 or 7 cross 7 with the help of the sequence of 3 cross 3 filters, because our goal is in convolutional neural network is to enlarge, right, the receptive field especially, and that can also be possible with the help of sequence of 3 cross 3 filters, right. If you are using 3 cross 3 filters, so it can also give you the same impact of 5 cross 5, because it can also help us in covering, right, the 5 cross 5 receptive field in the input image. So that was the major motivation behind this. And similarly also GoogleNet, ResNet, DenseNet. In ResNet, you will find the application of residual connections, skip connections, which are very, very important even in designing segmentation models, right? Especially U-Net, which is one of the most popular architecture in segmentation. We'll talk about it. What do you mean by skip connection, right? So you all know, what do you mean by skip connections or residual connection, I hope, right? And what are the advantages of these residual connections, right? So similarly, there is something called as a dense connections, a dense block that has been proposed in DenseNet, right? And these are very popular. So till date, if you go through the literature, right, people are still using this ResNet and DenseNet heavily, even MobileNet as well, right? So this is a recent architecture, right, published in CPPR. These are all actually, right, you can say the models that has been proposed, published in several top conferences. And this ConvNext is a very, interesting article. If you go through this article, you will also find that they have claimed that even convolutional neural network can beat Vision Transformer, although Vision Transformer is more dominating nowadays. But if you want, you can just go through this paper, right? And this is just a modification of this residual architecture, and they've introduced some new modules into it, right? For obviously for enhanced feature representations and all. But till date, if you go through the applications of computer visions and image processing, right, so you will find that the ResNet and DenseNet is the most widely used, architectures to solve several problems. Although it was developed on ImageNet dataset, which contains natural images, but we will find the applications of this ResNet and DenseNet in medical imaging, in agricultural field, even in analyzing the remote sensing images. So there are a couple of applications where you will find ResNet and DenseNet are used for learning the features, right? So now the question is how to use then this kind of architectures. So can we design our own architecture? Can we design our own architecture? So it's not that easy actually to design our own architecture, because while designing your architecture, you must be first focusing on the intuition behind the design of the new architecture, right? What is the intuition behind it? So why are you, designing this architecture? It's not like, somebody has developed, let's say, 8-layer architecture. So you will just simply increase the number of layers from 8 to 18, then you will claim that this is my architecture. It's not like that. So it's not correct all the time, right? So always increasing the number of layers, doesn't give you better results. Right? So those kind of experiments or those kind of analysis also you will find in the ResNet paper, that where the authors have claimed that even while you are increasing the number of layers doesn't always lead to a better performance, right? But with the help of residual connections, they have claimed that yes, residual connections may help you in going deeper and deeper and deeper, and because you are trying to preserve the features of the previous layers. That's what this residual neural network is all about. So okay, I will not spend much amount of time over here, because this part has already been covered, I hope so. So let us also talk about some of the limitations, right? Some of the limitations of working with convolutional neural network. As I mentioned, in convolutional neural network, that most of the architectures demand huge number of parameters, always in terms of millions. So then, how to optimize those parameters, right? So optimizing these parameters is itself is a top task, right? And at the same time, there are a lot of hyperparameters we have, right? So how to also tune those hyperparameters along with the parameters is, of course, a challenge. And as we all know that, yes, if you have more number of parameters, and mostly we don't have much amount of data, if you're dealing with several applications like medical imaging and all, so where you won't get a lot of data. So in that case, what you will do is there is a possibility that your model may suffer from overfitting issues because the number of parameters are huge compared to the number of samples, right? So yes, at the same time, the training time is also very, very long, and you need also GPU kind of systems, right? GPU enabled systems to train the models, right? So that means it all requires a huge amount of computational resources, right? So these are some of the concerns actually while we are working with convolutional neural networks. Here is some of the examples, like AlexNet takes 60 million parameters, as I already mentioned. So VGG takes 138 million parameters, right? So although the idea was good, right, by the authors of the VGG net, that to use 3x3 filters without using 5x5 or large size filters like 11x11 or 9x9, which actually leads to a less number of parameters, but the usage of the three fully connected layers at the end containing 4096 neurons, 4096 neurons, and 1000 neurons for solving 1000 class classification problem, because ImageNet contains actually 1000 number of classes. And these are the actually reasons, right? These three dense layers actually is the main reasons why they have 138 million parameters, right? So you can see, AlexNet also, AlexNet was designed or implemented using two ZTX 583 GB GPU, and it was taking 5 to 6 days to train the model. Similarly, VGG was taking 2 to 3 weeks on 4 NVIDIA Titan Black GPUs, right? So that means it's really huge, right? If it takes, sometimes if you want to make some changes into the architectures, you need to wait for 3 weeks, right, to get the result, and then come back to the model, and then you have to make some changes in the model, and then you need to train the model or retrain the model, you can like. So it takes a lot of time. So how to overcome these kind of problems, right? So yes, there are some strategies through which you can handle these issues to some extent, like instead of initializing the weights randomly, because as you all know, we've already studied traditional neural network, where also we initially initialize, right? We randomly initialize the weights and biases initially, and then we need to optimize the weights with the help of the algorithm. So instead of actually taking the random values, what you can do, you can just follow some of the initialization techniques, right, which has been shown to be provide good results over some sort of diverse data sets. Like Glorot and He initializations are some of the techniques which can be applied which can be applied instead of taking the random values, right? And you can just explore these kind of initialization techniques instead of taking the random values. Also, sometimes, as we all know, that these convolutions are nothing but filter-based techniques, right? So where you want to convolve the filters with the help of these inputs. So what you can do, though, because we all know from the image processing, right? Image processing, we all know that yes, there are different types of filters, like age-based filters, and there are also other types of filters like Laplacian filters and all, right? So those filters can also be used initially, but if you are having domain knowledge, if you are a domain expert, so what you can do, instead of taking the random values, right, initially as the coefficients for the filters which you are using for extraction of the features, you can just take some sort of like age-based filters like this, -1, -2, -1, right? So like this, 1 to 1, like this. Let's say this is one of the filter which I can use, right, initially. So instead of taking the random values, right? But you need to be an expert in the field of let's say this kind of things. You must have domain knowledge actually to design this kind of filters, right, manually. So it's hand designed actually, right? So we don't know whether we can correctly choose or not, but if you want, you can just take it, right? So you can just take different, as it is mentioned over here. So you can take different age-based filters with certain orientations and then shapes as well, right? You can also take some Laplacian filters, which is used to sharpen the image, or you can basically especially sharpen the kernel areas, or you can say the boundary regions of the objects and all. That may also help you, right, and end up with less number of epochs, or compared to the traditional one. Several regularization techniques also can be explored or can be used, like dropout. You might have heard of something called dropout, data augmentation kind of thing. You can use to overcome, right, the overfitting issues when the number of parameters are high compared to the number of samples. But this actually doesn't help you in making the training process faster, right? But yes, to some extent you can solve the problem. So what are then what we need to do here? Yeah. So as I mentioned earlier, that yes, CNNs are having some interesting properties that because it has a lot of hidden layers. So the low level, right, or especially the initial layers, right, in the convolutional neural network provides low level features, and then the middle layers provide us middle level features. And I'll talk about what you mean by this low level and high level features over here. And the later layers especially provides us high level features. So that's why we call sometimes CNN provides low level as well as high level features or hierarchical features, right? So these initial features, especially these low level features, contains generic features, right? What do you mean by generic features? Like edges, color, blobs, right? So these are like constant. These are like constant. Even if you will train the model on different data set, similar kind of features you will get, right, from the models. So, but the high level features especially are like more specialized features, and these are like data specific, right? So if you change the data set, so probably this kind of features is going to change. But these type of features remains constant even if you change the data set, right, for training the convolutional neural network model. So this is a very important concept to understand, right? Because our main goal is to actually understand the concept of transfer learning over here. So what are the different ways to use convolutional neural network for solving any task, right? Whether it is classification, segmentation, doesn't matter, right? Because everywhere you can just use the pre-trained models. The model has already been trained, right? You can just take, or you can just transfer the knowledge from those kind of pre-trained model, which has been trained on some source task, right, to solve a target task with the help of a algorithm, right? You can just transfer the knowledge from the one architecture to another one. I'll talk about it in detail, right? Transfer learning. I'll just spend 2 to 5 minutes right, transfer learning, and then we'll directly jump to the architectures which are used for solving segmentation tasks. Fine. So as I mentioned, that yes, there are two ways, especially to use convolutional neural network for solving actually, or for image or video analysis, as I mentioned, right? One is like training from the scratch. One is transfer learning. Training from the scratch is like AlexNet or ResNet or VGGNet. You have to design your own model, right? And then you will train it from the scratch. That means you will take all the coefficient values or the weights and biases of all the filters, right, randomly, and then you will apply the backpropagation rule, right? With the help of the optimizer, you will optimize all the parameters, right? So you have to train from the scratch with the help of your data only. Although this kind of approach looks accurate, right? Because you have to train the model by looking at your data, but it actually demands huge amount of data, right? So training from the scratch always demands huge amount of data, at the same time high computational resources. So that is why, as I already mentioned, also designing the model from the scratch itself is a top task because of also these reasons, right? Because it also demands huge amount of data as well as computational resources. So what is more popular nowadays in solving many problems is transfer learning, right? So in this case, actually, it requires comparatively less amount of data and computational resources. So what do you mean by transfer learning here, and why it is so popular nowadays? Yeah, so I mean, in case of traditional learning, or you can say, traditional machine learning and all, so given a different task, we usually design different model to solve different tasks. So these are, let's say, 3 tasks given to a task 1, task 2, task 3. So for different tasks, we usually design different kind of learning systems. But in case of transfer learning, let's say you are given, let's say you are having some model which has already been trained on some source task. Now, what is your goal is to solve a target task with the help of similar kind of architecture. Let's say you want to use this kind of architecture which has already been trained, so you can just transfer the knowledge from this architecture to this architecture to solve a target task, right? So that is what is actually transfer learning is all about. I'll also tell you that how we can practically solve this problem, right? So yes, we have, as I mentioned, a lot of models like ResNet, DenseNet. Those has been trained on huge data set. You can say a large data set or large scale data set. And can we use, because the kind of features they have learned on those kind of data set is like containing, let's say, 2 million images, having 1,000 classes. So probably they might have learned some important features at different layers. So can we just refine, can we use those features that has been learned over this ImageNet data set directly, or can we refine the features, right? Refining the features is a bit easier compared to learning the features from the scratch. Fine. So that was the actually main goal behind this transfer learning, and how to actually perform this transfer learning. And of course, as I mentioned, that this will help us in requiring less number of data as well as pure computational resources. Fine. So then how to use those kind of models, right, to solve a similar type of task, let's say, right? Different types of tasks also somewhat similar. And it all depends upon actually the kind of data you are using, what is the size of the data set, and as well as the similarity between the target and the source task, right? Okay. So let's say this is one of the architecture that has been developed on ImageNet dataset, fine. And you want to, and ImageNet is, let's say, is a data set having, let's say, 2 million images, around 2 million images, and having 1,000 classes, right? On this data set, this model has been trained. Now, you want to solve a same, image classification task, let's say, for simplicity, I'm taking. And these are all natural images. And here, I have also an image classification task, but the number of classes is 10, right? And all, let's say, natural images. So what you can do here? And the data set is pretty small. Data set is like, let's say it is containing, like 2,000, 4,000, or 5,000 images like that. There are 10 classes. So what is my goal here? To transfer, to use actually these architectures via transfer learning. I want to use these architectures via transfer learning. How is it possible? First of all, the last layer contains 1,000 neurons in this architecture because it was originally designed on the ImageNet dataset, which contains 1,000 classes. Now I'm only having 10 classes. So what I can do, I have to replace this layer with C number of classes, where C in this case is equal to 10. Fine. And then you have to look at different scenarios. So what are the constants here? So like, you need to first check whether your data set is large or small. If your data set is small and the source data and the target data similar, right? So try to remember all these points, which are very, very important here. What I'm saying, if the data set is small and the source data and the target data is similar, so what you can do, you have just now replaced the last layer, and you can just fine tune, or you can say reinitialize the last layer, and you can just freeze all other layers. Why this is going to work in this case? Because the data is almost similar. If the data is similar, you all know that these are initial layers, which usually gives us generic features, and these are all later layers which gives us specialized features. As I'm saying here, the data in case of the source data set is same as the target data set. So including or along with the generic features, the specialized features are almost same because the data is almost same. In that case, you can just freeze all layers in this particular convolutional neural network, and you can only reinitialize the last layer, right? If it is a small data set and the source data and the target data is similar, then you can just follow this. And if you are having a large data set, and if the source data and the last, the source data and the target data is somewhat similar, so what you can do here is you can just train a few layers, right? And you can just freeze the rest of the other layers. And if you're dealing with a large data set, let's say in this case, if you want, you can also fine tune all the layers. If you find that, yes, there are some differences, right, in the data. If you're having large data, then you can just go for fine tuning or readjusting the weights of the more number of layers, right? Not only these 3 layers, you can also go for fine tuning this many layers. If you want, you can fine tune whole layers. It all depends upon the kind of data which we're dealing with, right? So this is the simplest way actually to transfer the knowledge from one architecture to another, right, to solve a target task. And it all depends upon that. If you want to find out that is how many layers I have to readjust or reinitialize, then it all depends upon the kind of data which you are dealing with, even the data set size as well, right? Now let us directly move on to the segmentation architecture, convolutional neural network transformer, which is used to solve segmentation task. And here is the evolution, right? It all started from 2014 when this FCN came into the picture, known as fully convolutional network. I'll discuss in detail how it looks like and how it, how it is different from the traditional convolutional network, which is used for classification task. But this is the architecture which has been developed for solving semantic segmentation task, where every pixel has to be categorized or every pixel has to be assigned a semantic category, right, including the background. See, in the FCN also, people have used VGG16. That's what I was mentioning, right? So in FCN, people have adopted VGG16 architecture and they modified something, right, at the end, and then it finally becomes a segmentation-based architecture. So then in 2015, the most popular architecture, U-Net, was proposed. And U-Net was originally designed or implemented on medical imaging dataset and later been extended to, several computer vision datasets and all other datasets, you can say. So similarly, you will find something called as SegNet, DeepLab v3. Over the years, lot of variants of U-Net architectures. As I mentioned, U-Net is very, very popular. So people have thought of modifying these U-Net architectures by inserting some of the skip connections in the encoder, in the decoder, dense connections in the encoder, decoder, sometimes dense connections along the skip connections, right? And the names are like different. Sometimes res U-Net, dense U-Net, U-Net plus plus, res U-Net plus plus. And there is something called as attention mechanisms, attention U-Net, where attention mechanisms has been introduced into U-Net architectures and all. So similarly, we'll also find there are certain architectures, right? When this vision transformers came into the picture, then people started incorporating the concept of the transformer into the U-Net architecture known as trans U-Net. So similarly, there are different variants of vision transformer models available in the literature. So similar kind of a concept has also been you can say used here in U-Net architectures, and the names are like Schwinn U-Net architecture, DS trans U-Net, and several others. Right? We'll see. We can also see many of the architectures are very popular even if they are applied on medical imaging datasets, right? So including the U-Net architecture, which was actually published in a very top conference known as MICCAI, one of the top tier conferences in the field of medical imaging. So this paper itself has got more than as well. But that is, U-Net is so, but there is a need of where there is a need of output image, right? Where you want to generate the image with the help of this convolutional neural transformers. Fine. So this is how actually the fully convolutional, or the very first architecture, fully convolutional neural network looks like. And if you look at this one, right, this looks very similar to the architecture which you have just now seen, like VGGNet architecture. They have adapted, right? But you know that in VGGNet there are 3 layers, right? And here they have used a data set where there are 21 objects especially, including background, right? So that means every pixel has to be classified into 21 number of classes. So what they initially did, why the name is so-called fully convolutional neural network. Initially, they replaced all the dense layers, like these three are the dense layers, if you remember, right? So 4096 neurons in the last fully connected layers, and the last one was containing 1000, if you remember, right? But it was replaced by 21 because there are 21 number of classes, as I mentioned, including the background. And these dense layers is especially replaced by 1x1 convolutional layer. So there is nothing called as dense layer or fully connected layer right now, and these dense layers are replaced by 1x1 convolutional layers. With last 1x1 convolutional layer contains 21 filters, right? Or you can say where you can say it is actually C plus one number of channels, or you can say, or the channel dimension for the last 1x1 convolution, or you can say the output after this last 1x1 convolution, right, is nothing but C plus 1, where C is the number of classes, 1 is for background, right? So that's why the name is so-called fully convolutional neural network, because all layers, contain convolutions. There is no content layer over here. Yes. Question. I can see somebody has raised her hand. Yes. Please, you can write your queries in the chat box. I'll also discuss in detail, actually, right? So, I mean, why there is a need of C plus one number of channels in the last layer, right? Before actually getting the segmentation map. Yes, you can write your query in the chat box. Probably someone has raised the hand. So shall I wait or shall I move on?
I think no one is asking any questions. So do you want to continue or you want to break 5 minute or 10-minute break?
Yeah, I'm unable to. Hello.
Hello. Yes, sir.
Yes. Now you're audible. Yeah.
Sir, you want to 5 minute break or you want to continue the session?
Okay. I mean, even participants are also asking for break, so we can take a 5-minute break here. So
Okay.
then I can continue from here.
Sure, sir. Sure. Yes. Yes. Sir. So participants, we will just resume this session after 5 minutes. Just you can take a break.
second session over.
Hello. Hello, People sir. Shall we start, sir?
Can we start?
Yes, sir. Yes, sir.
Okay. Yeah. So I hope my screen is visible, right? I've already shared my screen.
Yes, sir.
Okay. So we were talking about actually the first architecture which was developed, dedicatedly developed for solving image segmentation task, nothing but called as fully convolutional neural network, which adopts VGG network, and at the end of VGG network, they replaced the fully connected layer or dense layers into 1x1 convolutional layer, and the final layer actually was having 1x1 with C plus 1 number of filters, where C is nothing but the we have. Also, we'll discuss. So if you remember, if you remember the kind of example which we have chosen is like there was a person riding bicycle, if you remember, right? In that case, so the number of classes are like person is one of the class, bicycle is one of the class, and plus 1 means here it is the background. So that means C is equal to 2 and 1 is like it is totally, in total, the value is 3. So the final layer will be having 1x1 filter, right, with 3 number of filters, right? 1x1 filter size, obviously, and 3 number of filters. And then is our goal here, right? Is our goal here is to get back and segmentation map, right? We want pixel-wise predictions. So that means the output image size should also be same as the input image size. But in case of VGGNet, what you have seen, right? What you have seen is, yes, we have used pooling layers, right? That means downsampling layers to downsample the feature maps, right? And there was also, intuition behind it, so it also reduces the number of parameters in the architecture. But directly using VGG architectures, even by replacing 1x1 filters, right, cannot solve our problem, segmentation problem. So what you need to do here is you need to upsample the feature map. In FCN, they have only used one stage or only one step of sampling, right? So after converting the after converting or after applying the final 1x1 convolutional filter, right, with channel dimension 21, they have used an upsampling layer. So we all know that upsampling can be done in multiple ways, even using the traditional interpolation techniques. But the kind of convolution they have introduced is transpose convolution, right? So it is known as transpose convolution. So it is just different from the standard convolution. Standard convolutions, if you are using unpadded convolution, unpadded, basically if you are not choosing the padding value, so while applying a filter, right, over an image, so you get just a a output which is little bit, right? Let's say my image size is 256 cross 256, and I'm using a 3x3 filter over here. And if you are using unpadded convolution over here, so then what you are getting is after convolution is 254 cross 254. That's what you know, right? 254 cross 254. Yes. And if I'll use 5 cross 5, so probably it will be 252 into 252, like that. Right? So always you get a reduced version. But if you just take the padding values as 1 here in this case, so you will get the same size output, right? But transpose convolution is something very different. So it will work, it will just work like upsampling operations, right? So even if you are having, let's say, image size 128 cross 128, so if you want to get back 256 cross 256, so you can use upsampling operations, that's what you know. And you can also use, in that case, transpose convolutions. So it is sometimes known as op convolutions, but deconvolution is not the correct word to use over here, although in the literature we'll find this the word, but deconvolution is something very different, right? So in signal processing, so you can either use transpose convolution or op convolution as the correct terms, right? Or which can be done using convolution operations, right? So they have only used one transpose convolutional layer at the end to get this kind of output. You see, final feature map is having 21 channel dimension, right? And it is having size similar to the input size. So this is actually the output which you will get from the convolutional neural network, and from where you can get this kind of map, right? So that means for every pixels, it is a pixel level classification problem, as I mentioned earlier. So for every pixel, you will get 21 values. For every pixel, you will get 21 values, if you remember, because there are 21 number of classes. And then again, based on the maximum value, and these are like the probability values. And that's what you also know from the image classification problem, that for every image, if you are solving, let's say 21 class classification problem, for every image you will get a 21 dimensional probability score values. That means in the final layer you will be having 21 neurons, and every neuron will give you a probability score value because you are using softmax over there. So then based on the maximum probability value, you used to assign that yes, this belongs to this class because this class is nothing but this neuron is giving us the highest probability value. But here, every image you were getting one probability values, but as I mentioned earlier, that here it is a pixel level classification problem, not an image level classification problem, right? So every pixel you will get, for every pixel you will get 21 classes. That means whether the pixel belong to object number 1, object number 2, and so on up to object number 20, or else it is the background. I hope you got my point. So similarly, every pixel you will get 21 number of values over here. And I'll also talk about the kind of loss function you are going to use here. Fine. And this is also one of the major limitations, that they have only used one upsampling layer, that is one transpose convolutional layer, to get back, right, the output size or output feature map size equal to the size of the input image. Fine. Then there is something called as ShegNet, right? One architecture which is very, very popular architecture comes with the picture, right? Which was earlier designed in 2015, but later it got published in IEEE PAMI, right? So if you look at this architecture, this is the first fully convolutional encoder-decoder architecture. Right? Now you will see that, yes, this is a little bit uniform. And this is where actually the encoder-decoder architecture got very, very popular. Right? What is this? This part is encoder. Encoder could be any, you can say, can be taken directly from any classification based convolutional neural network architecture. So it could be VGG, it could be any architecture, but they have adapted VGG without FC layers. So there is no FC layer. No need to even convert FC layers into 1x1 convolutions and all. They have only chosen the convolutional layers from the VGG, and they have just considered it as an encoder. And there is a decoder part over here. This decoder is nothing but simply the mirror of the encoder part, right? The way you have downscale, or you can say downsampled the feature maps in the reverse. So in the decoding, so you have to also get back the original image just in the reverse order. That's why I said that the decoder is the mirror of the encoder over here. Now, there's one question here: how to perform upsampling, right? Because the encoder obviously encodes the image, right, at different scales or at different levels. And then how to, right, get back, right, the output size, equal to the input image size, because that is what is our goal. And the final layer, of course, before the final layer, you'll be having 1x1 filter having 21 classes, right? 21 classes. Why? Because the kind of data set where it was implemented has contains 20 classes, or one is for background, right? And if you are solving, let's say, that particular task which we discussed, there's a person, there's a bicycle, and for this you have to take 3 classes over here, right? The channel dimension of the final layer should be 3. So in this case, it is 21, right? Because for every pixel you want to find out the probability scores for 21 classes. That's the fact. So how they perform upsampling over here, right? So they have not used any transpose convolution. They have not used any interpolation techniques. So what they did, you can see over here. So these are these red colors, right? Blocks are nothing but here upsampling operations they have done. So then how did they perform the upsampling operations over here? So during encoding process, they have stored the winning pooling indices, right? The winning indices they have stored, and then they have used those corresponding winning indices, the corresponding layers, right, to upsample the, you can say, the feature maps, right? So during encoding, we all know during encoding, right? So what are let's say max pooling operations have been applied over VGGNet, and you all know that how max pooling operations are applied over a window size 2x2, and stride is, let's say, 2x2. So let's say out of these 4 values, you have to say the maximum values. right? So you have to also store the winning indices. Let's say the winning index is this one. It's like, let's say 0, 0, 0, 1 is the position of the winning index. That you need to remember, that you need to store somewhere. And you can use this. You can use this index, and rest of the values will be 0 actually in case of decoding, right? You need to store these indices, winning indices, and you will take the help of these winning indices, right, to enlarge or to upsample the feature map. Right? So this is the concept actually that has been introduced in SegNet architecture, and rest others are same. Right? The learning procedure, the last layer will contain 1x1 filter having 21 classes. Everything is same. Fine. So then, at the same time, there is an architecture called UNet was also proposed. So we'll see what is the difference between this UNet and the rest of the architectures which you have seen, especially with fully convolutional network. So how this UNet architecture looks like. It is also a fully convolutional encoder-decoder architecture, but with skip connections, right? With skip connections. This is the major difference between actually UNet architectures and the other architectures which you have seen, although it was encoding and decoding. Also, there are some other differences. Here also, there is an encoder part. So this is how actually the UNet architecture looks like. It is having both encoder part and decoder part. You can see over here. So in the encoder, you can adopt any classification network, right? And the decoder, in the decoder, in place of saving the winning indices for the pooling operations, right? In the UNet, so they have used something called as again the off convolution operations, which we discussed. Off convolution or the transpose convolution operations. And again, the decoder is a mirror of encoder here. But in addition to process, right, the feature maps in the decoding process, it is also taking the features from the corresponding encoder path with the help of the skip connections. So these are like skip connections. Why this is actually important? Why these skip connections are important here in the decoding process, right? Because in the decoding, if we don't have any skip connections, what we usually do, or we usually apply a lot of convolutional operations followed by the pooling operations, right? And finally, what we are getting is a embedding informations over here, right? Or you can say the final features, and those features are again right upsampled, right, with the help of transpose convolutions followed by some of the convolution operations to get back the segmentation map, or you can say the final feature map, from where we can get this segmentation map. So why there is a need of this skip connection? What is the importance of it and how it helps? So if you look at here, the skip connections, right, from the corresponding, these are the corresponding path. Let's say you can say this is stage 1 unit, this is stage 2, this is stage 3, this is stage 4. So similarly, we have similar number of stages over here in the UNet or in the decoder, you can say. And what we are trying to do here is, right, so instead of only taking these features for the processing in the decoding, we are also including the feature, the corresponding features from the encoder. This helps actually in preserving the localization information which has been lost, right, while processing it through different levels. And what we usually do, it is very simple. We usually concatenating the features, right? It is also helping us in preserving important informations of which are lost during this, and that's why it helps in improving the localization informations, right, in the decoder part. So how it is performed? So you need to only take the features from the corresponding encoder layer and concatenate that features, because both are having same size, right? You can just concatenate them together and then further processed by some of the layers, convolutional layers. And same process you have to repeat for all the stages, right? And you can also, if you want, you can also check without having the skip connections. You can just remove the skip connection, check the performance, and you can just take this, take these skip connections, right, along with the other connections, and then you will check the result. So you'll find a huge difference between them, right? Because this ultimately helps in, and then these skip connections are very, very important over here. Over the years, people have introduced, different types of concepts, or you can say different types of modules, connections into the UNet architectures to get several variants of UNet. So, like for example, right, what do you mean by a skip connection, right, or a residual connection? So, in residual connections, you all know that series of convolutional layers followed by a residual connections, right? It has a lot of importance. You can reuse the features, which is used for feature reuse. It preserves the spatial information, whatever was there in the early layers. At the same time, it is used for better feature flow and gradient flow in the architecture, and it sometimes also helps in reducing the vanishing gradient problem, right? So this is a residual connections which is introduced, or you can say residual block, which is introduced in ResNet architecture. And the same type of thing can be also introduced here in UNet. So what you have to do, you have to only, so these are the two actually convolutional layers applied. You have to only introduce a residual connections. So just introduce a residual connection over here. Every stage you have to introduce a residual connections, and this unit has become something called as RES unit. Right, I can show you the architecture. So this is how actually the RES unit architecture looks like. You can see, I mean, still the the shape of the architecture is like English letter U. That's why the name is so-called UNet. And here it is just like this. So just people have represented in multiple ways, right? Not in this manner. So this can still be considered as a unit, although the orientation is different here. Fine. So you can just see here, this is the input. Convolution, as I mentioned, followed by addition like this. This is the skip connection. You can see the residual connection. Then there is a max pooling operation over here, or you can say downsampling operations followed by the same thing, right? Convolution followed by addition. That means the same residual connection. There is a residual connection over here. Residual connection, right? So this is how the architecture of RES unit architecture looks like, right? So and then if you and then later also people have introduced dense connections into this different kind of layers. So what do you mean by dense block? And then it is known as dense unit architecture. So people have just incorporated the concept that has been introduced, right? Or evolving the convolutional neural network architectures, and the same concept has been also introduced here in the unit architectures, and also they have shown that yes, this kind of connections, right, is helping us in improving the performance on several data sets. If you want, you can also go through all these architectures. The coding is very simple, and you can also easily change the code, and you can get RES unit architecture, dense unit architectures, and several other things. Including these connections or the components, researchers have also introduced something called as an attention mechanism. Also, okay, there's another architecture called as UNet++, where you can also find that in the skip connections also people have introduced. So previously in the skip connections, right, there was no layers and all, there is no components. So later people have also introduced in the skip connections, there are like convolutional layers, in even residual connections among them, dense connections among them. Even people have introduced something called as attention mechanisms into this, right, to focus only on the important regions while suppressing the irrelevant regions. That's what also people have done, right? So I will not discuss much about the attention mechanisms in detail, right? So, but I'll just give you an overview. What do you mean by attention mechanisms, and why we're interested in attention mechanisms, and how it how by incorporating these attention mechanisms helps in improving the performance of the convolutional neural network, especially. And the kind of vision transformer model which everyone is talking about nowadays is nothing but an attention mechanism based model, right? Where you will find the application of self-attention mechanism, right? Which is very, very important nowadays to extract global context from the images, because CNNs are very good at extraction of the local informations, because the convolution operation itself is a local operation. It all depends upon the neighborhood, right? The kind of value which you are getting is all dependent on the neighborhood values. That's why it is localized, or it gives us localized informations or local informations, but it is not good at extraction of the global informations, right? How a particular region of the image is related to or dependent to other regions in the image. So for that, actually the self-attention is playing an important role, and therefore VIT is very good at extraction of the global contextual features from the images compared to the convolutional neural network. We'll see later on some of the VIT, or you can say vision transformer based models, right? I mean, obviously designed based on the architecture of UNet. So attention mechanisms, okay, so as human beings naturally and effectively find salient regions, right? So I mean, it's natural to human vision systems, right? So I mean, if I just ask you, let's say this is an image given to you, and if I ask you a question that what is the boy doing? So obviously you will only focus on this region, and because other regions are like irrelevant for us, right? So you will only focus on this region, and you will simply ignore all other regions, because my question is something called as what is the boy doing here, right? So we need to only pay attention to the important regions and also ignore the other regions as well, because the other regions may contain some redundant features, right? So that's why you need to pay attention to this particular kind of important things. And mathematically also, attention mechanisms are easy to understand, not very difficult. All right. So the goal is simple to enhance the feature representation capability of the model, so that the model can only focus on important features, and can also suppress the irrelevant and redundant features. This is also very, very important and very close to the concept of explainable AI, where you can explain why is your model performing better, why is not why is your model performing better, and why not is your model performing better? So like that, right? So that means you can, you can just enhance the thrust factor of your model. Let's say if you are working with medical images, right? If you just, go with a set of quantitative values, or even the doctors are not going to be happy, right? Because they don't know what you mean by 99 accuracy or 95 accuracy or 90% accuracy. So what they will ask is, how can I trust on your model? So showing some values, I cannot have trust on your model. So you have to also showcase the that where the model is going to focus given an image, given a medical image. Let's say where you want to identify the tumor location. So whether the model is also focusing on the tumor location appropriately or not, right? So this is where actually we'll also find the applications of the attention mechanisms, where attention mechanisms will help us in focusing on those important regions. So it is just an, we can say, an weighted multiplications, right? You need to learn some weights adaptively. It can be called as an adaptive selection process, right? Where you want to select some of the features by providing some weights. So attention mechanisms, this definition is written over here. An attention mechanism can be treated as a dynamic selection process that is realized by adaptively weighting features, as I mentioned, right, according to the importance of the input. Yes, that all depends upon the kind of problem which you are solving, right? So, if you go through the literature, you will find this incorporating these attention mechanisms significantly improve the performance of several computer vision tasks, as I mentioned, because it is very, very important nowadays. So attention mechanisms in general are of actually two types: hard attention, soft attention. But technically, if I say so, attention mechanisms, which has been introduced to convolutional neural networks, are of specially two types. One is channel attention, one is spatial attention. And sometimes you will also find the combinations of channel attention and spatial attention together. And if you're dealing with the video data, so probably you'll be having something called as a temporal information, or temporal attention, right? Because there is one more dimension in the video data. And what do you mean by this channel attention and the spatial attention? Why the name is so called? It focuses on what to attend, it focuses on where to attend. Especially when we apply, there are a set of images given to us, and you apply a convolutional neural network over here. So set of convolutional layers and all, and finally you are getting, let's say, some feature map, and these feature maps are processed through a classifier at the end, right? So when you get some feature maps either from the last layer or from any layers, let's say, right? So every feature map, right, is having dimensions, right, like height, width. There is something called as C. C is nothing but the number of channels. So channel attention and spatial attention are the two types of attentions which has been introduced over the years, and there are various ways actually to find out the channel attention scores and spatial attention scores. Even the kind of self attention, which is the major core component of vision transformer, is also a kind of spatial attention, right? I mean, I'm talking about the standard self attention one, right? So people have also later introduced something called as channel wise self attention. Even we also did some work on it, right? So this kind of output always you will get, and these are like feature maps for us, right? So what do you mean by channel attention? Here you need to highlight the important channels, right? Out of C number of channels, you need to highlight the important channels and suppress other channels. So how to do it, right? So you must have C number of weights, right? 1, 2, and so on up to C, right? So you must have C number of weights which can be multiplied with all the channels, right? It's like a weighted multiplication, but I want just these weights to be, right, learned with the help of the backpropagation algorithm, or the algorithm which we have, right? So you'll be having C number of channels, so you'll get C number of values. So how to make it adaptive? You will just take it as a, you can just apply 1x1 convolutional layer or a fully connected layer over here. Again, you will get the same value of C dimension 1, 2 up to C. And then to just get a weight value, you can apply a sigmoid, right, which will give you a value between 0 to 1. It is like a weighted multiplication, right? The highest, the maximum value. Let's say if you are multiplying 0.8 into some, channel, so probably that channel will be highlighted properly. And if you are multiplying with a small value, that will be suppressed. Like this, it is just a, multiplication of the weighted values. So after this, applying the sigmoid operation, you will get different weights. That's a different weights for C number of values. And these weights will be multiplied element wise with all the channels, with all the channels over here. And then what you will get is a channel, and these weights are sometimes known as channel wise attention weights, attention scores also you can say. And after multiplication, again you will get a feature map having size HWC over here. So how to get actually the C values? Just by applying a global average pooling over all the channels. So for every picture map, if you apply global average pooling, you can just get a single value. There are various ways to do this. This is the simplest one I'm talking about, right? People have also used, multiple ways to get this. People have applied global max pooling over here to get another set of C values. Then they combined these two weights together to get a final weight value, then multiply together to get this channel one. So what we're trying to do here in channel attention, we're trying to focus on the best channel because not all the channels are important for us. So we want to only highlight the important channels, not on the other channels. So similarly, spatial attention says here that which of the positions are important for us. So you need to again multiply, right, some of the weights, but in this case, the weights will be two-dimensional weights, not the one-dimensional weights, right? Two-dimensional weights, because you have two-dimensional positions over here, spatial positions. Every positions will be having one weight, right? So just try to go through these papers. Like squeeze and excitation is the first, channel attention paper where you will get the information about this channel attention and all this. There's something called as CBAM, BAM. These are all like the attentions where both channel and spatial attention have been used together sequentially or in parallel manner. That also you need to check how to use both, right? Both channel attention and spatial attention together, because when you are combining, then there is a possibility that you may combine them either in sequential manner or in parallel manner. That also you need to check, right? Okay. And there is something called as a self-attention, which is something different from this because these are like local attentions, right? And self-attention is like for every position, you need to find out the relationship every other positions, right? So in that case, although the weights will be 2D, right? The attention weights will be 2D, but the size will be something called as HW into SW, right? So what do you mean by SW into SW? So here it is like the spatial positions. If you look at here, so the height, it is H stands for height here, W stands for width. So SW is nothing but the total number of pixels we have. So you want to find out that how every position, right? How every position in that particular feature map is related to every other positions, right? So this is why it is known as, right? Pairwise. It gives us pairwise feature dependencies or feature relationships. And as you are computing the relationship between one feature with all the pixels or all the features, so that's why it gives us global information as well. So this is the concept that has been introduced in Bayesian transformers to encode the image and ultimately gives us the global informations, right? Or find out the relationship among the pixels, right, in a global context. Fine. So yeah, so attention mechanisms, as I mentioned, have also been introduced in U-Net architectures. You can see over here. Somewhere you will find its applications either in encoder or in decoder, or somewhere even in the skip connections. And this is the paper, actually, the first paper where attention has been introduced into the U-Net architecture, right? And it was implemented on a medical data set. You can just go through this paper to know more about it, how they have introduced the attention modules or attention gates over here, right? And how it helps in focusing on the important regions, especially the pathological regions, right? And suppress the other regions. Very, very important. And also gives us precise, helps us in giving the precise boundaries of the pathological regions, or you can say the tumors and them. ResUnit++ is another architecture where you can see the application of both residual connection as well as squeeze and excitation, which I just now mentioned. These are like the attention mechanisms, especially the channel attention mechanisms that has been introduced after each stage of the encoder. And they have also shown using this attention, right? They've got better results, right? Compared to the architecture without attention. Fine. So this is just I'm showing you that how you can introduce attention mechanisms and how people have introduced, right? So we have just now talked about some of the limitations of the CNN-based approaches, that it cannot learn global contextual informations. Only it is good at extraction of local. So that's why VIT came. VITs came into the picture, which can easily handle the global feature dependencies. But VITs are again, not computationally efficient, because it sometimes, I'm talking about the standard, right, vanilla VITs, because it demands a huge amount of data, as well as it leads to high computational requirements, right? So sometimes in some of the applications, you cannot directly think of applying VITs, so you need to modify something, right? So because in case of, let's say, medical imaging and all, so it is difficult to directly jump from this one particular natural imaging area to this area, because you don't have much amount of data, right, in case of medical imaging. So as I mentioned that, yes, CNNs are very good at extraction of local informations. VITs are very good of extraction of global informations. So VIT is also having some advantages of extraction of global information, but it should also have the capability to extract local informations as well. So I need to then combine together like CNN and VIT, known as convolutional VIT. Right, so that's what actually we did in the past, right? So we developed a couple of convolutional transformer models where we combined the benefits of, or the strengths of both convolutional neural network and VIT together, so that it can extract both local as well as global information together, which are very, very important for a particular task. Yeah, there are two architectures I think I have kept related to vision transformer. One is a UNet-R architecture. You can see over here. So UNet-R is you can say it is an architecture, transformer-based UNet architecture, where the traditional transformer concept has been introduced. Like initially, the image is divided into certain patches, and all those patches will be flattened. And basically, you have to apply linear projections, and then there will be something called as position embeddings. Together will be sent to the transformer encoder, where you will find the applications of this multi-head self attention. These are nothing but self attentions applied several times over here. And then you can see in the decoder they have only used some sort of convolutional layers, but the encoder part is fully transformer over here, just to learn the global context from the images that did this. So you can just go through this paper. It was published in WSCV 2022. And mostly targeted on medical data set. Later, this kind of architectures has been also used in several other computer vision tasks. The architecture that was published is known as TransUNet. So instead of taking the patches directly from the images, right? So initially, what they did is they have just used a set of convolutional layers or convolutional neural network they have employed over here to get the patches, and then those patches are again project linearly, or especially they have applied linear projection, and then they have sent all those patches to this transformer encoder, which is similar to the previous one, which I've already discussed. But there's one limitations over here, that every time you need to convert these patches, two-dimensional or three-dimensional patches, into a single vector to process through these our transformer layers, right? So again, in the output, you can see especially in the decoder layer, you can see they have also used upsampling layers over here, right? Obviously, upsampling layers, and always there will be some 1x1 layer at the end with C+1 number of channels, right? C is equal to number of classes, already discussed. And they have also combined, LGC, they have also tried to combine the convolutional features along with the features which they have extracted from the transformer, right? Just to make it, less local and global, right? Just to have local and global information together. That's what actually was their plan. And if you want, you can just go through this paper to know more about it, right? I think there is another session on transformers, so probably then you can easily understand what you mean by this self attention and all, and how this transformer works differently from this convolutional neural network. Because if you go through the vanilla transformer or the traditional transformer, so they don't have any convolution operations. So later people have introduced convolution operations into the transformer architecture known as convolutional transformer. Okay. So now let us talk about the kind of loss function. I'll only talk about one type of loss function. So you can, if you want, you can just explore. So I've just written over here. So various types of loss function we have. So what kind of loss function, right, we can use over here? So what kind of loss function is used in classification problem? May I know? You can write your answers in the chat box. Yes, please. So what kind of, okay, cross entropy. Okay. So can I use a mean square error as a loss function for solving classification problem? Why we're interested in cross entropy? Okay, I can see the answer no, sir. So can you just tell us why? Why no? And what this cross entropy does? So let me tell you the answer also quickly, because I think we have to stop after some time. So a lot of contents to convert to discuss, right? So what we know that this mean square error basically tells us, right, how let's say y is the our target output and y cap is the predicted output which we are getting from our model. Yes, absolutely correct, Preeti. Thank you. So it measures the deviations from the okay. So basically, what we actually from mean square error, what we usually find out, right, is like how much y cap is deviated from this y, right? So it doesn't actually tell us how one probability distribution is differentiated from another probability distributions. So what we are ultimately getting, I mean, I'm talking about classification problem right now, then I will, right, extend the concept to the segmentation problem, right? So in case of cross entropy, actually what we are getting ultimately by by passing a set of images, let's say, or whatever the input may be, through a convolutional neural network, what we are getting ultimately is set of probability values, that is y cap, right? Let's say this is one probability distributions which we are getting, and we know that we cannot directly use, right, the the labels. The labels has to be initially converted into its corresponding one-hot encoding. This is also a kind of probability distributions, right? So this is the target probability distribution, where if you add all the values, you'll get the value 1. So similarly, if you add all the values in y cap also, you'll get the value 1. This is also a probability distribution. This is a probability distribution. This is a probability distribution. So now you want to find out the difference between two probability distributions. This cannot be directly computed using probability, mean square error. Mean square error is not meant to find out the distance between or the differentiation between two probability distributions. So to find out the probability, the difference between the two probability distributions, so we have something called as cross entropy here. And this has been actually, you can say, derived from something called as relative entropy concept. So if you go through the entropy formula, then you will find something called as relative entropy, and then you will find called as cross entropy. And we all know the formula, right? Yi log of yi cap. That's what we know. This is a, where I varies from 1 to c. C is the total number of classes. That's what we know, right? And this is actually categorical cross entropy, where the number of classes are more than 2. And at the end, final layer. So even the activation function is also dependent on this. If you are solving a regression problem, the activation function, the final layer will be a linear one. And if you are solving a classification problem, right, the activation function will be a softmax one. Even if you are solving binary classification problem, in that case, the activation function could be sigmoid, but in that case, you have to use binary cross entropy as a loss function. Right? If you're using softmax, so then you have to use categorical cross entropy as the loss function. Right? So these activation functions are dependent on the problem statement which you are solving. So, but in this case, actually, in the segmentation, can I use, my question here is, in case of segmentation, can I use, cross entropy loss function? What will be your answer? In case of segmentation, can I use cross entropy as a loss function? Is it possible to use? Yes, sir. Okay. So of course, so you have to find out the loss for every pixel, right? So the kind of loss function which you can find out here is sum of pixel-wise cross entropy. What does it mean? Because for every pixel, you are getting a probability distribution, right? So what you can do, so that's why I've written, so you have to find out the pixel-wise cross entropy and you have to add them together. That's what is known as sum of pixel-wise cross entropy. Again, if you want, you can use sigmoid activation function if you're dealing with only 2 classes, right? And if you want, you can also, use a kind of softmax activation function if you are dealing with more number of classes. Even if you are dealing with 2 number of classes, you can also use softmax, right? You know that. So I've been, while solving a 2-class classification problem, right? while solving a classification problem, I mean, basically two-class classification problem, either you can use 2 neurons in the output layer, or also you can use 1 neuron in the output layer, right? So 1 neuron, sigmoid, binary cross entropy is the loss function. For 2 neuron, it is softmax, and spherical cross entropy is the loss function, right? Okay, if you have any queries, actually I'll discuss at the end of the lecture. Let me first finish the contents which I plan to cover in this particular session, right? So there are also several other, different types of loss functions. Please go through it carefully. Some of them are distribution-based loss function, like we discussed. And some of loss functions are very important. Even in case of classification as well as segmentation is known as focal loss function, very, very important. Even weighted also, balance loss, cross entropy, these are important when you are dealing with an imbalanced data set, and which is a common issue while solving real-time problem, as you all know, right? Because there is possibility that the classes are imbalanced. So how to deal with this with the help of loss functions, right? There are also a couple of other approaches through which you can deal with these issues. Coming to the performance measures, it is a little bit different, not like classification where you can directly use accuracy as a measure. We cannot use, actually, if you want, you can use accuracy as a measure over here, but we don't want to use accuracy as a measure here, right? Because accuracy also, accuracy is not a good measure in case of segmentation. Please try to explore it. Why I'm saying accuracy is not a good measure. So we have something called as Dice coefficient, which measures the overlapping between the ground truth as well as the segmented image. So we'll be having one ground truth image, and we'll be having one segmented image which you've got. So then try to find out the overlap between, and also you can find out the intersection of a union between the regions, right, which is of our focus. That gives us something called a Jacquard coefficient, or intersection of a union. We have also several other measures. Please go through it. If you go through the papers also, you'll get to know about it. Now I'm going to showcase some of the case studies, right, on, of course, medical image segmentation, which we have been working with. So one of the interesting problem statement is, polyp segmentation. So polyp is one kind of, you can say, growth which is formed in the inner wall of the colon, right? And it leads to colorectal cancer, right? Which is one of the third most common cancer worldwide if it is not detected at an early stage. So this polyps, right, initially, which is benign in nature, may lead to colorectal cancers. So it is very, very important to identify the polyps at the right time. But identification of the polyp itself is a very difficult task. And if you go through the recent literature, if you go through the medical papers, so you'll find that the miss rate of the polyp detection by the doctors is too high compared to the others, right? It is 6 to 27%. The miss rate is very, very high. If some of the polyps are missed during examination, right? Then what will happen? That colorectal cancers, because initially the patients don't have these symptoms. These are like asymptomatic, this kind of thing. So why it is challenging? Why polyps are missed during colonoscopy examinations? Right? Because of its mutations in shape, size, and sometimes polyps are very, very similar, or this texture, right? So let's say this is like polyps. So these polyps are having textures. You can see over here there's a problem. It's very, very difficult to identify even the doctors, right? So there are even some cases I will show you where it is very difficult to identify the polyps because of its camouflage properties, right? So having similarities with the surrounding tissues, and as I mentioned, the high similarity with the surrounding tissues, and sometimes less adulate textures. You can identify which is polyp. The texture of the polyp is right, and that is why the miss rate is really. So what is our goal is to design some efficient algorithm here to identify the polyps and ultimately help the doctors to keep a proper boundary of the polyps. Sometimes even the boundary of the polyps is a similarity with the, because of its similarity with the surrounding tissues, right? And there can be also multiple polyps present in a single gram. What does it mean? So polyps can be 1, polyps can be even more than 10, it can be even beyond that. So there can be multiple polyps that are present in an image. If some of the polyps are missed, then also those kind of polyps may lead to colorectal cancer. So what we have to do here is, we have developed something called as a multi-scale convolutional transformer model, as I mentioned, right? So combining this convolution and transformer together have the benefits of both convolutional neural network as well as VIT together, right? Of extraction of the local as well as global information, right? I mean, basically global Yes. And also, we had something called as the self-attention, as I mentioned. So, initially the self-attention which was designed, it was designed through the one-dimensional vectors. At the time, people have also designed the self-attention which can be applied over multi-dimensional data, 2D and 3D data. So, as I mentioned, also initially, the self-attention for extraction of the spatial relationship or global spatial relationship. So here we have also introduced how to find out the global channel relationships, how one channel is related to every other channels. That is what also we have introduced over here. So both channel-wise spatial attention as well as spatial-wise self-attention has been introduced here, and they have been taken together, to give the global relationship along the spatial direction and the channel direction. At the same time, if you look at the encoder over here, so there is a skip connection, but there is no component in the skip connection over here. And in the encoder, if you see here, we have introduced something called as a multi-scale feature extractor, where we have not used different filter sizes like standard convolutions to get the multi-scale features. Rather, we have used separable convolutions, and I hope you know what I mean by separable convolutions. I mean, basically, instead of 3x filter, we can use two one-dimensional filters in 3x1 and 1x3, which will lead to less number of parameters, right? The outproduct of these two, right? Because these are two one-dimensional filters, so the outproduct of these two one-dimensional filters should give us 3x3 filter, right? Similar to the standard 3x3 filter. But if you are using standard 3x3 filter, it's a 9 parameters. So if you are using two one-dimensional filters, you'll be having parameters. But we know that with high dimensional filters and number of filters in the convolutional neural network, that also ultimately helps in reducing the parameters, right? So separable convolutions has been introduced here of different size to extract the feature set to different scales, are having different sizes, right? As I mentioned earlier, so to capture those information, something called multi-scale feature extractor, followed by an attention mechanism like channel attention and spatial attention. You can see over here. And the decoder part, in the encoder, we have not used any transformer, but in the decoder, we have introduced transformer, right? So this is the self-attention architecture, right? And then we have introduced something called the transformer architecture in the all decoder stages. And this paper was accepted in IC 31st conference. Name is processing, one of the largest and very old conferences in the field of IC. And also our paper has been identified as top 5% papers, right? In this particular conference, right? So go through our paper. Although if you want the code of this paper, we are ready to share the code with you, right? Because we have actually the say. I think we have released the code of this particular paper. So if you want, you can also share the code with you. Probably available on the GitHub, so I need to check. So here are some of the results, and these are some of the architectures which we have validated by ourselves on the benchmark data sets. There are some architectures which I already mentioned, like UNet, SegNet, ResUnit, Attention Unit, ResUnit plus all architectures I discussed, right, including this UNet R. I think I did not discuss something called as DeepLab, which is a very popular architecture. Please try to go through this one. DeepLab is also very popular, right? I will share the link of the paper, definitely. Sure. I mean, you can see in many cases we are getting better performance compared to the models, right, which we have validated or compared with. So here are some of the results on different data sets you can see, and yes, some of the qualitative results we have, you can see, right, on the different kind of polyp images taken from different data sets, right? You can see over here, this is the ground truth image provided by the doctors. This is the output which came from our model, and these are some of the outputs, right, for segmentation maps. Here we are only having one class, and there is one background here. Only you need to identify polyp, whether every pixel is polyp or background. That's what is our goal here. So there are all cases where there are two polyps, exactly these cases, and if you look at the output, right, and the boundary of the polyp is pretty similar to the ground truth image. Here also in this case, the boundary is pretty similar, but if you look at the output of other models, it is not good, right? Because the boundary is very, very important to resect the polyp, right, by the doctors. So yeah, this is what we have got, and what we have also found later on, right? I mean, this paper was with one of my master student, Niladri, right? And later we found that yes, this kind of model can be used in real-time clinical settings or not. So for that, the model should have better generalization capability. You know that. So what do you mean by generalization, right? So how to use the kind of model which we have designed to generalize, basically to check the generalization performance, right? So how to, you need to check that whether your model is performing better on the unseen data on which the model has not been trained. Probably the unseen data may be captured from different demographic regions, even using different image settings, right? Different imaging devices. So then we thought of designing something called as a model which is known as right SIAM based. SIAM is one of the most popular architecture till date, right? I mean, you can say one of the foundation model because people are looking at now designing foundation models for classifications, for segmentation, even for all other tasks. So segmentation anything model is one of the founding model, right? One of the foundation model you can say, right? Designed for segmentation task, and but it cannot be directly adapted to medical imaging domain. Although it is high generalization performance or zero shot generalization capability, but it cannot be directly adapted to medical imaging because of the lack of domain expertise or domain specific knowledge, because it was originally validated on natural images. So how to then adopt this kind of architectures to generalization performance in the field of medical image analysis? Then we thought of because fine tuning, right? Previously we discussed transfer learning, but transfer, even if you are using fine tuning concept over here, fine tuning of this SIAM also leads to high computational cost and memory requirements as well. So it is actually designed with the help of Bayesian transformer, right? It is a prompt based segmentation task. I don't have time to discuss much about it, but I'll just show you one of the architectures recently published and in a top conference known as WACV 2025. And you all know, right? So WACV is one of the top tier conferences in the field of computer vision. So this is what we have developed. Actually, I cannot go in details in this particular architecture. So actually, what we usually do is, as I mentioned, that even if fine tuning of SIAM, right, on the medical data takes a lot of time and memory requirements. So what we thought of, why not to introduce something called as adapter modules into the SIAM architecture, right? So adapters are like those modules which can help us, right, adapting to new domain, and you can just fine tune the adapters without fine-tuning the SIAM model, and those adapters by injecting the information into the SIAM encoder, or you can say the VIT kind of encoder, right? And we have designed an adapter module, something called as Mamba-based adapter module over here, known as Mamba Prior, where we have, and this Mamba is nothing but an alternative to what you can say the vision transformer nowadays. So which is helping us in extraction of this long range dependencies at a linear time. It is actually computational efficient compared to the vision transformers, right? So we have just introduced something called as a Mamba-based prior over here, and in adapter you can see over here I have used different notations. Like, so these notations are like trainable, and we have made the SIAM encoder Trojan. In addition to that, we have this module actually especially we have developed. In addition to that, our learning is happening here in two different stages, because SIAM based model always is a prompt based segmentation. As I mentioned, it demands prompts in the form of mask and something else, bounding boxes and all in the decoding process. So, but we know that in real time we won't have a mask, we won't have any bounding box and all. So then we thought of why not to generate something called a pseudo mask. So then what we do, actually what we do is we usually generate the pseudo mask with the help of the encoder, and then we use those pseudo masks to get to basically train the prompt encoder as well as the SIAM decoder. That's what actually was the goal behind it. And if you want, you can just go through this paper. This was recently accepted, and this paper is already available in arXiv. If you want, you can also go through the paper in detail. Yeah, here are some of the results, as I mentioned, on the seen data sets, right, with all of the popular architectures. I can show you the results on the unseen data set as well. These are some of the unseen data set which I have. Unseen means the model has not seen any of the samples from this particular data set, right? Taken from different demographic regions with different images. These are all recent powerful models, and from here, all the models are transformer based, and the rest of them are CNN based, right? Only I have compared with UNet and UNet++, and rest others are like all powerful models. You can see the results which we have obtained. Not in all cases, getting all best. In some cases also we're getting second best results like that. Here you can see the results, right, on the scene data set. The model is already seen, right? These images, I mean, not these exactly images, these are images, right? The model has seen the images of this particular data set. And now you see, in particular, this image, where is the point? So doctor has said that this is the point, but I don't see there's here. So everyone will look at this point and definitely model other models would not be able to take. This is how we can actually develop that, right? On scene data sets. So similarly, we have outputs on scene data sets. You can see over here. These are all right from on scene sets, not the images from the data set. Over here, you see 300:dv, and it is nothing but the three different data sets where we use for only generalization purpose. You can see particularly this image, where is the, you can see if you look at this particular image, you will not be able to find out the polyps because there is nothing, you can't even see it, right? So the experts have labeled that yes, there are two polyps. Our model even could not able to identify, right, whether there are two polyps, even the boundaries, although it has been identified that yes, there are two polyps, but the boundary has not been correctly identified, right? So recently, we have also proposed something called as a boundary-based distillation module. And same module is something called boundary-based to cover this kind of issues, or how to find out the better boundaries for this kind of scenarios where evidence is not given to us, right? So we have introduced something called boundary destination modules. So we've got a paper also recently in MICCAI, right? So if you want, you can. I'll just make it public today itself. Our paper. So MICCAI is where actually the unit was published, right? So before we have introduced something called as boundary module, right, into this kind of architecture, which is giving us even better results in these cases, right? If you go to the paper, you will find in these cases, even the boundary module helps in giving better results. Fine. So another also I have another set of I want to discuss in details another applications. Let me quickly discuss the zero shot learning process, right? I mean, which is also one of the focus of this lecture. I'll just give you the idea behind right, what do you mean by few shot learning. So let me. So I think we have 7 minutes. Can I continue up to 7 minutes, up to 12:30?
Yes, sure, sir. Sure, no issue. Hello.
Yeah, I'll just give you the fundamental idea behind right, few shot learning, which is also one of the focus of this lecture. Yeah. So when I say few shot learning, what does it mean, right? So you need to first also understand, right, the different learning scenarios, like starting from supervised, semi-supervised, and all. So what we all know that yes, deep learning models is heavily dependent on the huge amount of data, right, for effective training. That's what we know. And if I give you small amount of data, you won't prefer deep learning models, right? But human visual systems, right? Human visual systems, right? Can recognize new classes with extremely few levels. I mean, that's what is the power of the human visual systems. Even if I show you two pictures of a particular person, so probably you can easily, right, recognize that person, right? Maybe after 2 days or after 3 days, right? But for a model, it is very, very difficult. For a deep learning model, it is difficult if a particular class is having only one sample or two samples or probably three samples. It is very difficult for a model, right, to identify or that particular person or that particular you can say level, right? So yes, if when there are less number of samples, huge number of parameters, people are using regularization technique to solve the overfitting problem, but that is not our solution here. Our solution is something very different. Even you might have heard about something called as semi-supervised learning, where not all images are labeled, right? You are having a data set where some of the samples are labeled, most of the samples are unlabeled. So how to generate the pseudo levels to solve the problem, right? But in case of semi-supervised learning, there is a requirement that all classes must have labeled images, must have some labeled images, right? So and then there are, let's say, there is a data set having, let's say, 10 classes. So 10 classes from C1, C2, and C1 up to C10. Every class, right, will have some sort of labeled images. And there are so many unlabeled images. That is fine. And you can just generate, labels, pseudo labels for all these unlabeled images. And then you can just perform this semi-supervised learning task. But now the question is, what to do if this is not the case? What does it mean? So that means if there's a possibility that a class can have only one sample, a class can have only two samples. Even there's a possibility that a class may not have any samples, right? In that case, what you have to do is you have to look at something called as few-shot learning algorithms. So what do you mean by this few-shot learning? And then I will talk about what you mean by one-shot and zero-shot learning. Right, and also I'll show you the overview. What are the possible methods we have, and then you can go through those papers. I've also, I think, kept a few papers for you, and then you can just go through those papers to have an idea. It's a very interesting problem statement, right? So, what is our goal here? To train the models capable of rapidly generalizing to new tasks with only a few samples. Right. I'll also give you one example of face recognition. Right, and even several other examples also. Right, where you are only given one image, let's say one image per person, a particular person, and based on that you need to design a model, and ultimately you want your model to generalize well onto the new task with the help of only a few samples. Sometimes it is one sample, sometimes 0 samples, sometimes few samples. So that means we have limited number of samples for few classes, and for which you are predicting the class levels, right? And for which we want to find out the predictions. You can also see over here, right? And it is actually very close to the practical scenario. Even sometimes it happens that we have seen multiple instances of one class, even less instances of another class, but still we could be able to recognize, right, those classes which are having limited number of samples. So how to train the models, how to enable the models to perform similar to the behavior. Right? So you can have many base classes. You will be having classes with multiple instances or examples, and your goal is to design a classifier to perform well. But you want also to design the classifier to perform well on the noble class data. That means where you are having only few samples, right? So that is a bit difficult, but for a model. But we'll see how we can do this. So when to use then few-shot learning approaches? So this, when the data set is annotated, yes, data set is annotated, but all or some classes, mostly some classes, have very few training examples. That's what we discussed. Sometimes even there are some classes without having any examples, right? So we'll try to discuss what do you mean by one-shot learning, what do you mean by zero-shot learning, and let us first define what do you mean by few-shot learning. Let us say X is nothing but an image, or probably the features which we have extracted with the help of any convoluted architectures, right? And Y is the label. And the few-shot learning can be defined in this way, that you'll be having training set data like dtrain, which will be having the samples like Xi and Yi, where Xi is nothing but the input images or the features, you can say, and the corresponding label is Yi, and capital I is nothing but the total number of samples, right? So how can we define then this? It is a n way. How can we define a few-shot learning problem? So specifically, we can define a few-shot learning problem as a n-way K-shot, very important term, n-way K-shot learning problem, where n is the total number of classes we have, and k is, right? K is, especially we're talking about those classes, right? N is the total number of classes, right? And k is nothing but the number of samples with respect to those classes. Could you follow? So I'll show you also a few examples so that you can say that what do you mean by this n and k over here. So yes, we are given a set of images and the corresponding labels, right? And we can define a few-shot learning approach as a n-way K-shot few-shot learning approach, where we have only few samples, right? Like k. Sometimes this k value could be 1, sometimes the k value could be 0. So in case where k value is equal to 1, it is called as one-shot learning. When the k value is 0, it is known as zero-shot learning. I hope at least you understand the concept of n is nothing but the number of classes, right? For every class, you will be having one sample, that is one-shot learning. For every class, you'll be having, let's say the classes are having no samples. This is zero sort learning. And for every class, let's say you are having 4 images. So then you can call it as a 4 sort learning. So similarly, if it is 2 images, then it is 2 sort learning. Hope you got my points. And the rest of the classes, I mean, especially we're talking about those classes like noble classes and base classes are having sufficient number of samples. Noble classes are having limited number of samples, right? So there are different approaches through which you can solve the problems, or you can solve the few shot learning problems, including one shot and zero shot learning problems. One is the model based approach, which are known as embedding learning based approaches. One is data based approaches, sometimes known as hallucination and feature synthesis methods, where you might have learned something I called as Gyan yesterday, right? So you can just use, it is just known as feature, learning to augment. That means you can, learn, or you can generate the samples of the novel classes for which there are limited number of samples, and then you can just reduce this few shot learning problem into a simple supervised learning problem, right? So this is pretty simple because you can use generative models and all to generate the data, or you can also use data augmentation kind of approach to solve the problem. But we have something called as a algorithm based approach, sometimes known as parameter based approaches. I'll only focus on one particular type of approach, which is model based approach, and sometimes called as meta learning based approach. So what do you mean by this meta learning over here? I have one example for you, right? You can see. So a boy is looking something, some animal right in the zoo, but he's not able to identify what kind of animal it is because he has never seen this kind of animals before. So he's asking you that what kind of animal is this? So then what you can do, so instead of directly telling the answer, right, instead of directly giving the answers to the boy, so what you can do is you can just give a set of cards, right? So here is the set of cards where these are sometimes called a support set, right? So here is the set of cards given to the boy, where for every class, for every category, there is only one sample. And now you ask the boy to find out, right, to find out the class level of this unknown sample, or of this query image, you can say, right? So this is actually meta learning, right? So given a query image or given a support set, you need to identify the similarity of this query image with these support set images, right? So that's what then obviously the boy will check the support set, and then they finally then he can say maybe this is an otter, right? So this is how actually meta learning is different from actually the supervised learning. In the supervised learning setup, so we all know that you'll be given a set of training set, and you will design a model, and then the test samples are nothing but are the samples which are never seen before use or never used during the training process, and the test samples are always from the known classes. This is the supervised setting. The test samples are always from the known classes, right? We don't have any unknown classes over here. So this kind of test sample is given, so you can directly, you have already learned a model, so you can say yes, it belongs to Husky category because it has the features matching with the samples of the Husky category. Although it looks different, I mean, but this class has already been trained, right? The many samples of this class has already been trained. But in case of few shot learning, we have some query samples over here which the model has never seen, and the query samples are from the unknown classes. So then we are having a training set having categories with a lot of samples, but we have a query samples over here. So you will be given something called as we're talking on only one type of algorithm, right, which is meta learning. And I already mentioned that you can also deal with this kind of problem with the help of data-based algorithms like generative adversarial neural network and all, right? So you'll be given again a support set over here. So what you have to do, so you have to find out the distance especially, or you can say similarity between the query sample with the support sets. So based on the higher similarity, you can decide the class level, right? So this is how actually we solve here the few set learning problems with the help of meta learning, right? It is just learning to learn, right? You are learning a model to learn new things, right? So you'll be given a support set, and as I mentioned, NUA is represents the support set has n number of classes, and K sort is like every class has K samples. It's very easy to understand. So if you look at this particular example, here I'm having 4 classes in the support set, and every class is having 2 samples. So that means I can call it as a 4-way 2-sort problem, right? So similarly, I can have 1-sort learning problem where I'll be having only one sample with respect to each class, right? So that is known as 1-sort learning approach. one-shot learning, if we go through the literature, we'll find there are different methods to solve one-shot learning problem. There is something called as Sandwich network, very popular to solve even face recognition and face verification problem, where application face recognition comes under this category, where for every there's no necessary that every sample or every person have multiple number of images. Every sample can have only one images, or every person can have one images, right? You cannot solve directly with the help of traditional convolutional neural network, right? So, and then maybe during the test time you will have an image, right, here, and then you need to identify the similarity of this image with respect to all the images, right? And then if the similarity score is right, if the similarity score is high, then yes, they are similar. If the similarity score, I mean, that's what you need to check actually, whether the similarity score is high or similarity score is low, right? So, I mean, I was talking about why we cannot solve this with the help of convolutional neural network, why it is not practically feasible. Let's say there are only 4 persons initially. So you designed a convolutional neural network having 4 neurons, right? So let's say that there are few more persons joined your company. So then you have to again change the what I can say, whole model, and you have to reinitialize or you have to retrain the model once again. So you can't do it all the time, right? So you can have this kind of Siamese kind of network where what we can do for one particular image, you can just design a convolutional neural network, and then you can have a feature embedding, so you can just extract features from any layer, and then you can have test sample for, again, you can also apply the same architecture. It is the same architecture you have to apply for the query sample, and you will get something called as feature number 2, and then you can find out the difference between this feature and this feature, right? With the help of, this is a feature vector. Maybe this is a one-dimensional feature vector if you're collecting from the last layer, right? If you're collecting from the last layer, not from the softmax layer, just before that, right? So then you have to identify, the difference between these two, especially the similarity. So for similarity, either you can use the Euclidean distance, also one of the measure, or you can just use any kind of distance measure to find out the similarity, right? And then if you just go through the Siamese network, it's a very interesting architecture that has been adopted, right, for solving this face recognition and verification problem, right? So this is a kind of Siamese network which you can see over here. So that this is the already sample given to us, and this is a query image. So you are just trying to find out the relationship between this and that. Yeah. So when I say the number of ways are more, I mean the number of classes are more. That time there is a possibility that the accuracy may degrade. It is, of course, right, when there are, let's say, if I saw the boy only 2 classes over here, right? Instead of 6 classes, if I saw the boy only, let's say, a hamster and otter, so he can easily pick out otter, right? But if there are 6 classes, you need to match with everybody, right? That's why. So if the number of classes are more, so there's a possibility that the accuracy can be also degraded. If the because 3 ways easier than 6 way. That's what I mentioned right now. I just mentioned 2 way, but it is 3 way in this case. And if the number of sorts are more, right? Sorts means the number of classes, the number of samples for each class, then the prediction accuracy is going to be very good. That is also, but in real time. So I mean, while zero sort learning, so we do not have even a single sample, right? A single sample in case of a particular class. So as I mentioned, the 2 sort is easier than 1 sort because there are 2 samples at least. But in 1 sort, we're having only 1 sample with respect to 1 class. So yes, it's easy, as I mentioned. That will be having a couple of images, maybe query image, maybe a maybe the images which are already given in the support set. You have to identify to a function, especially with the help of you have to learn a function, especially with the help of convolutional neural network, and then you need to identify the similarities with the support set, right? Comparing with the query with every sample with the support set, then identify the similarity score, right? Identify the similarity score of this image with all the image. It is 0.03, it is 0.05, and now if you look at here, this similarity score for this class is higher compared to the others, right? So even in case of zero sort learning, there may be questions, right? Sir, how we will solve the problem, right? Because we don't have any other information about the classes. So in case of zero sort learning, we not only consider the images, right, as the input to the model, but also some text descriptions and some other summaries as well, right? So that means in addition to the features, visual features, we must have to provide additional information, right, which will describe the image perfectly. so that this can be useful later on in case of zero-shot learning. So zero-shot learning is a little bit difficult. You all know that because you don't have any samples, right? Even in the support set, right? Yeah, here are some of the references you can go through. This is one of the survey paper, right, which you can go through, from where you will get to know more about this, few-shot learning. To start with, actually, you can just focus on the data part, right, because this is very, very easy to solve this kind of problem, right? And then you can directly jump to the meta-learning based approaches. And there are also a few other approaches over here. One is the meta-learning based, and one is also data-based here. Generating networks for zero-shot learning. For every algorithms you may have, zero-shot settings. You can also have one-shot settings. You can also have, what I can say, few-shot learning settings. Right. So that's all from my side. Thank you very much for your patient listening, and I'll be happy to take any questions if you have.
Thank you, sir. Am I audible, sir?
Yes, you're audible.
Thank you so much, sir. So I think they have sufficient question on the go.
Oh,
So
okay.
still if you have
do I need to go through the chat box?
So there is no question or query.
Please share the link of the paper. I will share definitely. Any questions, Dr. Vikas?
No, sir. I think there is no more questions. So we might start with the next session.
Yeah, let me just share the paper which they're asking.
Just share the link, sir.
I'll just share the link there in the chat box.
Yes, sir.
So, if you have any queries, also you can drop me an email. No problem. I could see. Share the link of any tips, tools, or software to draw like these architecture diagrams for our research articles. Okay, interesting question. So, yeah, we usually draw this kind of pictures using Google Draw, which is a very simple one. You can also follow some other tools like Draw.io and all, right? There is something called Draw.io, Inkscape, and Google Draw. You can just follow this kind of things, and it takes a lot of time actually. So to draw a figure, it takes a lot of time. Sometimes even it takes even 2 to 3 days to complete one figure. So it takes a lot of time, but yes, ultimately that it is fine. So once again, thank you, Dr. Vikas, for the opportunity to speak. Dr. Surendra Hans for giving the opportunity to speak something or to share something in front of the participants. So thank you once again, Dr. Vikas, for the invitation.
Sir, it was a privilege for us to have you in the session, sir. I have one question.
Yes.
Sanjeev Das. Who is you may ask just quickly.
Yes, please. We are waiting. I think he's typing, right?
Maybe. Yes, sir. Please make it quickly.
Yeah, we can wait up to 1 minute.
Can you please suggest some hands-on where I can? Sir, one question is there.
Oh, sorry, I could not able to showcase. Yeah. So I can actually the way actually is written actually on the code. So I can share the code with Dr. Vikas. Although actually I have it, so let me show you. Although I planned actually to showcase the code with you, probably I don't get actually time for this. So I think I've already opened the Google Colab. So can you see my screen? Yeah. So I didn't get time to discuss all these things. But if you go through the code, you will see that UNet architecture. So whatever I discussed, it is having, let's say, 4 stages. You can see over here: convolutional layer by my max pooling followed by convolutional layer max pooling, nothing else in the code. It is very easy. And the decoder, again, there is a transpose convolution followed by convolution, concatenation, transpose convolution. Then you remember, right? Concatenation from the encoder, and then nothing but convolution operation. Same process is repeated, and the final layer, you can see over here, there is a 1x1 convolution. I'm dealing with two-class classification problem, sorry, two-class segmentation problem here. That's why I'm using sigmoid. But if it is more, then you can use softmax. Everything is same, whatever I discussed. And this is the model. See how easy it is to design the model. And if I want to just introduce a residual connection over here, you know that what I have to do, right? There are two convolutional layers. Let's say this is C1, this is C2, and I will write here C3 is equal to C2 plus C1, right? Even before C1, right? If anything is there, right? So just as before C1 is input, right? Second, like input plus C2 is equal to C3. That will become a residual connection, nothing else, right? So similarly, you can introduce dense connections. Let's say, you want to introduce something called as, attention mechanism. Then you have to define attention mechanism with the help of function. Then wherever you want to use attention, then you just call a function like a convolution function you are calling here. You just call another function here. Say again, C2 is equal to something called as attention. You can just write attention, and inside this attention function, you can just pass through the C2 on C2. Let's say C1. C1 is the output, and then maybe whatever the other parameters is required for you, right? So again, then I have to apply max pooling over C2 over here, right? Not C1. And if you want, you can also make it C1 as well. So this is why actually you can just introduce attention mechanisms into here. So even if you want attention mechanisms inside the skip connection, you can also do it. So how you can introduce it? So just while concatenation, right? During concatenation, so what you are trying, where you are trying to directly take the output from the encoder, just pass a function and then just concatenate. Then it becomes concatenation. So I mean, in a skip connection, you introduced a lot, especially attention mechanism like that. It's not that difficult, I think. So it's very easy, right? So either you can use TensorFlow or PyTorch. It's up to you which one you like, right? No, this is again a PyTorch implementation of the same architecture. You can see how actually the codes are a little bit different because it varies from syntax to syntax over here. So I'll share the codes of the unit architecture with Dr. Vikas. So Dr. Vikas will share with you. Okay, is that fine?
Yes, I think it would be fine for all of us. Yes, sir.
Yeah. So okay, thank you.
Thank you so much.
All.
Thank you so much, sir, for your time. So good afternoon all. I think it was a nice session, and let's start with our next session that was basically in continuation with the earlier one. Okay, so we are talking about RNN and the motivation behind the RNN. So let me first share my screen. So I hope my screen is visible.
Yes, sir, your screen is.
Thank you, Astos. So let us just recall what we have gone through till now. Okay, so basically we were talking about few things. Okay, we are just summarizing what we have studied in the last session. So we were talking about the feed forward neural network, CNN versus RNN. Okay, now as we are running out of time, so I was parallelly drawing this one. So let's look at the three scenario where the first one is just the FFN, the CNN, and here we are having the RNN. Okay, now suppose we are having the input, the same input that we have talked yesterday, we have discussed this one. So I have visited Jaipur in 2023, and the second one is in 2023 I have visited Jaipur. Now the question is, if I ask any machine learning algorithm to tell us in which year the particular हेलो हाँ सर मैं सेशन के बाद कॉल करता हूँ हाँ ओके सर So basically, if we ask any machine learning algorithm, in which year I have visited the Jaipur, so definitely if I use the feed forward neural network, how it will work is, suppose we are having this one input, okay, one sample, the other sample, this is one and this is second, so this is one and two. Okay, now as we know, CNN or any neural network does not work on words. So definitely we need to map it in the some numerical value, and there we talk about the embedding vectors or embedding mechanisms. Okay, so each of the means word will be mapped to some numerical values. You can basically go through some course materials on embeddings and how it why we basically do embeddings and what each value basically indicates. So that is a separate discussion on this one. But anyway, so we generally provide the embedded vector, but for the time being, just forget about this embedding. And whenever we talk about these three architecture, why we are coming up with these architectures? So basically, based on the application that we require. Okay, so suppose we are having a classification problem, or we want to predict some values, and there is no sequential ordering concern. So we may use this one. We may use the feed-forward neural network architecture variants of that FFN. Whenever we are having some image kind of thing, and we need a kind of shared parameter mechanism, so somewhat we can go with the CNNs. Okay. Likewise, if some application wants to learn the context of the inputs one by one, means whatever you have learned till now, you want to apply your knowledge to the next input at the next time step in that order. Okay, so there basically we have different example means architectures. So in feed forward neural network, if we talk about the parameter sharing, and if I ask you what the parameter sharing means, so what was the parameter sharing? What was parameter sharing? Just reuse of same parameters. Okay, now if we talk in terms of FFN, do we have a sense of parameter sharing? So if we just look at the weight matrix here, so definitely we can say they are independent, but at embedding level, embedding vector level, we can say yes, they share the same parameter, and that parameter is nothing but the embedded vector. Okay, so wherever this I will appear, or have will appear, or 2023 will appear, the embedded vector will remain same, will be shared across the parameter. But apart from the embedding, if so we are not concerned about embedding, so we are not talking in terms of embedding here. We are not talking in terms of embedding vector. So let's forget about embedding. Just suppose we are having the input like this. Okay, now we are feeding that input into our network. Now if I ask you how it will work, so we have already talked about the weight vectors. Okay, so let me for the first one, so that W will be something like, for the first input, I'm talking about this one, so it will be something like W11 and Wk, if k number of neurons are there in this layer. Okay, so now suppose in the first sample the I is here, or 2023 is somewhere here. Now in the second input the 2023 is somewhere here, while the other values are reordered. Okay, whatever we had in the earlier input, now it is reordered. So now as we know that each corresponding to each input, we are having a set of weight vector. So we are having another weight vector corresponding to this one. We are having another weight vector corresponding to this neuron. So we are having separate neurons, separate weight vector for each of the neuron. For this one, so for this one we are having some weight vector. Similarly, for suppose this we say W2, this is W1, and the third input neuron we say W3. So each of them is basically, so our W is nothing but this W1, W2, W3. This was the thing that we have talked in the last class, in the last session. Now, suppose we have fed this sample here. So here, the weight that will get updated or learned will be based on I, and this is the weight, the W1. But at the other time, the input sample is this one. So now, instead of I, we are learning this in. And now the weight vector will get changed according to this new input. So the weight vector W1 will get updated according to this in. Previously it got updated according to I, but now it will get updated according to in. So if we say that we want to design a machine learning model, and we have this set of input, and I wanted to know in which year one particular person has visited Jaipur. So definitely this particular context will not be captured, as each of the neuron is having separate weight vector. So here the true sense of parameter sharing is not there, as each of the input neurons are having different weight vectors, and if we are reordering the input, definitely the ordered value, they will be treated completely different. Okay, they are not going to be treated as same. So definitely this was because we have not shared sense, means we don't know, means this neuron is learning separately, this one learning separately, this one learning separately. If in some way, if we have combined the learning process, so ordering should have not mattered. This is where we basically trying to focus, shift our focus to some other architecture. So the next concept is CNN. Now the thing is, if I ask you, do we have the concept of parameter sharing here? Do we have the concept of parameter sharing here? Okay. Problem with the RNN. Okay, let me just go through this one. So we have already talked about the problem with the RNN. So as in the RNN, we go on unfolding. So the simple architecture was this one in the RNN. This was the input. This was, sorry, this was the output and the recurrent connection. Okay, so this suppose it is so we are providing input. Now suppose we are having a sequence of input, like I have visited Jaipur in 2023. So what it will do is, it will provide I, okay, then this function, whatever function we are having in the RNN, this will try to predict the output, the next word, okay, and whatever it has done internally, that is basically the hidden state, and that will move to the next state. Okay, now the next hidden state will have input as have, okay, and the another input is basically this HT. Okay, now here we have, and then we have input the previous knowledge from the previous state. So now this is again the same function, and this, suppose this is weight vector W. So we have the next input to the next state. This will go on with the sequence. So if it is time step 1, it is at time step 2, likewise it will go on. So the next one is visited, okay, and this is ht plus 1, and here we will have output, okay. So again, if we look at here, just look at the parameter sharing here, okay. I'm not talking about LSTM now, so I have just unrolled in the last session itself. So now, as the sequence of this input, the length of the sequence will go on increasing, this neural network will go on unrolling. Like, just look at here that we have talked in the last class. So this is the simple architecture of RNN. This is the hidden state, and based on the number of the length of the input sequence, it will go on recurring. It will go on unrolling itself. So we have also talked about this function f st minus 1 xt. So st minus 1 was nothing but this, we can say st minus 1, okay. So here I have written st minus 1, here it is st minus 1. Now if we go on increasing this one, so in next term we have talked about, if we write ht, so it will become w times this f ht minus 1 and your xt, isn't it? And if we solve for this one, and suppose the weight is w, so at last what we will have is h0 x0, and this will become wt. I have basically shown you in the last class. Now if this wt is diagonalizable, okay, so w could have been written like t u inverse, okay. And then we have talked about this diagonal matrix of eigenvalue. So this is the matrix, eigenvalue matrix, this is the eigenvector matrix, and inverse of eigenvector matrix. So if the lambda I is less than 1, lambda I is greater than 1, and lambda I is equal to 1. What was the case? What was this case? Anyone? Yes. So basically no parameter sharing with CNN filters. So basically in CNN filters, the kernel that we are using, the kernel, that kernel is a parameter that we are learning. So let me just first answer this one, the problem with RNN, then we will come to that next. So I think we have talked about this one. What will the problem here? What kind of problem RNN will face? What kind of problem it will face? Anyone? If you recall from the previous class? Exactly. Yes, it will be vanishing gradient. Why? Because the lambda value is less than 1, and then we are multiplying it over wt times, so gradually it will go on decreasing if this sequence is go on increasing, isn't it? As the sequence will go on increasing, this w to the power t definitely go on decreasing as we back propagate through time. We all know the we use the gradient descent, so we use the gradient descent from this step to the first step. So it will go on decreasing, and ultimately we may lose the value. We may not see any changes in the learning process from the initial stages. So this is the vanishing gradient. What about this problem? If the lambda value will be greater than 1, what will happen? Yes, so this is the exploding gradient, and in this case there won't be any change. So this was the problem due to the amount of information that we wanted to preserve through the RNA network. Okay, and let me come back to the what the parameters we talk about. And in CNN we don't have parameter sharing. So if we talk about the kernel, okay, if we talk about the kernel, so here what is happening? These next time it will again same. That is not the case. Okay, so that's why we say the shallow parameter sharing in case of CNN, okay, it is special in nature, while whenever we talk about the sequential model, we want to preserve the order of the sequence. But in this case, even though suppose some object is there and that the same object is here, the CNN will easily be able to identify that object, but it will not preserve the contextual information that it contained. Okay, so it will correctly predict that they are the object that this kernel is looking for, but what information they are carrying won't be preserved by the CNN. So that sequential preservation of information could only be attained if all of the whole image will share the same parameter. But when we move this one, the input will get changed, and again the filter will still be same, but input is getting changed. So input filter again get means it is only for just for neighborhood. But in this case, what is happening? Suppose this is the W. I have provided I as input. Okay, so this input will get multiplied something like let me just come to this example. So what will happen here? This input, suppose we have taken this input here, and this is the hidden state from the previous time step. So the previous knowledge we can say. So this F
Sir, can you hear me? I think we are having a technical issue. We'll be back in a minute.
Am I audible now?
Yes, sir. Now you're audible.
Okay, thank you. So what I was explaining, what was the last thing that I was discussing here? Anyone can please? The point from where I got disconnected? Okay, so let me just talk about this one. Okay, we were just talking about this value. Okay, so what we were talking about, RNN problem. Okay, so RNN problem we were talking about. So RNN problem. So this was the one that we were discussing. So I hope this was completed, or shall I explain it again? Shall I explain it again? Okay, fine. Okay, so next RNN problem was clear. The next thing that we were talking about, how the parameter sharing is there for in case of RNN. Okay, so this is what I was talking about. So basically we provide some input, we have output as usual, but then the next thing is we are having this this particular weight matrix shared across the hidden state. So if you look at the example here, so I think it is example not there for RNN. Actually, I thought it was covered, so that's why I have not put that example here. But anyway, I think the motivation for this RNN is clear. Why this RNN uh, uh, have or faces some problem of this vanishing gradient or exploding gradient. And now what we are going to change in this RNN is the problem was due to the long range isn't it? I think you all agree with this one. The problem was with that long range dependency. If we somehow we try to reduce this long range dependency, or we can say the amount of information if if we can control the amount of info that network carry, so definitely we will be able to reduce the effect of vanishing gradient problem, okay, or exploding, we can say. So to mitigate this problem, the authors have basically proposed a gated solution, gated network. Okay, now this gate is nothing but a mechanism to control, basically makes mechanism to control the information that we are carrying along the network, or the amount of unrolling we are having. Okay, so how much information we propagate from the previous state to next state, that will be basically be controlled by these gated networks. Okay, so whenever we talk about the gated network, now one more thing before going to this gated network. So there are various architecture that can that basically deals with this vanishing gradient problem, and one major architecture that nowadays is very popular is, apart from this gated recurrent units, that now most of you have heard the attention and transformer mechanisms. Okay, so whatever we are going to see in the gated recurrent unit, most of the thing have been basically avoided in case of attention mechanism. Okay, so let us go through this gated network. So in the gated one, we have two popular example, the LSTM and the GRU. Okay, now this LSTM, let us first go through this LSTM. This LSTM says that rather than having all the information flowing through this network, can we just control it through some selectively reading, writing, and forgetting. So the basic logic with this LSTM is, in our case of RNN, we had this scenario: ht minus 1, xt, this is some function we can say, and this was output. This is ht, same function, xt plus 1 is output, ht plus 1, xt plus 2, output at each state. Okay, so the thing was, we were having this hidden state information, basically the state information get propagated along the network. Okay, and now whenever we were back propagating, the gradient at each step will basically keep on minimizing this information. This is, suppose that, okay, this will keep on minimize this information. So whenever it will reach to the initial time step, definitely the value will be very smaller, this value will be very smaller, and the overall update will be very small. Okay, so the thing is, rather than passing the value or the amount of information that we have learned till this stage, can we control the information flow in some way or other way? Okay, so the one way is, we can go for the selective read, means how much information we want. Selective write means how much information. So let me just rewrite this one. So these three are basically implemented by three concepts that we will be learning. Okay, the selective read. The selective read is basically nothing but output. So suppose we are having, I'm just having one simple example. Okay, suppose, so in LSTM, in RNN, what we had is the previous state information, current input, and the weight matrices. Okay, now in case of LSTM, what we are having is, along with the previous state, we are having one concept of long-term memory. Okay, the current input will be as it is. Okay, and this previous state, we refer it as short-term memory. So why short-term memory? Because this is the value that was just computed before, and now it is being fed to the next hidden unit. So it will go on updated in each RNN unit. So now we are having three input. Here we are having two input, the one and the first and the second. Now we have something like this one. We are having one cell. Okay, we are having three input. Okay, some way we are considering, we say this one as C, the cell state at time t. This is the previous state. that is ht minus 1 or cell state at t minus 1, and this is the current input. Okay, so we are considering this ct minus 1, the ht minus 1, and this current input. So earlier for RNN this was the case, this was not there, but now along with the short term memory we are again having the long term memory, means the amount of memory that will go through initial step to the final state without any basically a gradient applied on that one. So we will see how it is being executed. So now the thing is we are going to unroll this one. So before going ahead, just let us uh, just recall this one. So there are three concepts: the selective read, write, and forget. Means now we are controlling the information the way we want to propagate it to the next level or next state. Okay, and these three operations are basically controlled using some gates, because this is gated architecture. So for that we have different gates: the output gate, the input gate, and forget gate. Okay, so let me just expand this example. So this is one RNN unit, we can say. Okay, this is one RNN unit. Now I'm just expanding this one. So just let me write it here. So this is ct minus 1. Okay, we have ht minus 1. xt. Okay. So this is forget here. So I hope I am audible here.
Yes, sir, you are audible.
Okay, thank you, thank you. Okay, so forget gate, I will modify, keep on changing this diagram so that the incremental approach will be clear here. The output gate, and then from here it will be ht. Okay, okay. So for example, means let us see here. So this is the short term memory. Okay, this is the short term memory that we have written here. This is the long term memory, the memory that is coming far from far in the from the initial step. Okay, now it is going directly from all the units that we are having in the recurrence process. So I have just expanded this one RNN unit. Okay, so in this RNN unit, how much information is going to be propagated or put on this line will be basically controlled, or how much information will be forwarded to as a short-term memory to the next RNN unit will be controlled by these three gates. Okay, so let me draw a better picture of this one. So this is your c t minus 1. Okay, so now just let's talk about this forget gate. Okay, this forget gate is basically the sigmoid activation function. And if I ask you what is the range of sigmoid function, we all know this is 0, 1. Okay, now so all the gates, the forget gate or the input gate or the output gate, all three gates will use this sigmoid activation function, and the region will be clear shown. So now just look at here, this is the input we are having at time step t, and remember I have just expanded this RNN unit where this was the sorry, I have forget about this ht minus 1. The same input will be forwarded to all of them, ht minus 1. Okay, ht minus 1, this was xt, and this was the ct minus 1. Okay, this we say the cell state or the long term memory. This is short term memory, this is input. I have just expanded this into this one. Means each of the RNN unit will have a three kinds of gates: the forget gate, the input gate, and output gate. Now let us talk about what this forget gate, input gate is doing here. Okay, so the forget gate, now if I ask you what this forget gate will do, so this is taking this forget gate is taking xt as input, ht minus 1 as input, isn't it? This forget gate will take the xt, the input at time t, and the short term memory from the previous state. Okay, and then if you have some biases, we can apply that biases also. Okay, so you can write the bias also, but anyway we are keeping it simple, so you can ignore this one. Now so the thing is, since I have said you that this is a kind of sigmoid function, so on this input whenever we will apply the sigmoid function, so it is nothing but sigmoid on xt, ht minus 1, and the vectors that we are using. Okay, suppose this is u1, v1, v2, v3, basically u2. Okay, so u2, and then the w will remains, suppose this is w1, this is w2, this is w3. Now you might say me that, sir, you have said that this w is shared across them, but you are writing it w1, w2, and w3. So actually it is like this one: w1, w2, w3, w4. Okay, or whatever number of parameters are, and this w will be repeated across the unit. So this is the one unit, the same thing will repeat again, the same RNN structure will repeat again, and the w1, w2, w3 will remain as it is. Okay, so I think there is no confusion in this one why I have written separately. Now if I say I apply some sigmoid function on some value or some expression, so definitely the value will lie within 0 to 1. Now so this is what we are having here. So this forget gate, suppose this will give us some output. Now what this value is indicating, if we say that we are multiplying the long term memory with some value, isn't it? And that value is coming from some sigmoid function. What will be your answer? What it is doing here? Any answer from your side? What it is doing here, the sigmoid? Hello? Can anybody tell me what is the answer? So keeping 0 to 1. So basically Yes, but how it is affecting the long-term memory, that I'm asking. How it is affecting the long-term memory. So basically, it is, suppose I'm saying 0. If the sigmoid value is giving us the 0, so what will be the final value here? What will be the transient value? The Ct minus 1. What will the value here? No, not important features. The amount of information from the long-term memory, isn't it? If I say that this sigmoid function, this forget gate has given 0, then definitely it will be some fraction multiplied with this Ct minus 1. So it will be like, we can say this is nothing but the percentage of information, or sorry, the percentage of long term memory to be preserved based on the current input and previous state. Is it clear what I am saying here, what I am trying to say? So basically, if this forget gate, in all of the gates are using a function sigmoid, so they will, in some manner, they will always give us a value between 0 to 1. Now, if I say 0, what does it mean? Means whatever value we are having at this side, this is element wise multiplication. So definitely it is going 0 this side. Agree or not? It will be 0 on that side. If it is 1, so all the long-term memory that we had will come this side. So it will become Ct minus 1 itself. Or if I say 0.5, what does it mean? What does it mean? If I say that output of this sigmoid function, the forget gate, is 0.5, what does it mean? Anyone please? Value of 0.5, how it will affect the long-term memory? Anyone please? Anyway, so it is saying that only 50% of the long-term memory should be forwarded next. Okay, so based on the previous state information, means whatever you have just learned and what is your current input, based on that, how much information that you want to keep on, like as a long-term memory, okay. Likewise, we had an input gate, okay. So here we are saying that we are having a fraction of long-term memory that to be preserved based on the current input and the hidden state value, okay. Now the next thing is, so we have controlled the amount of information that is going to be utilized in this RNN unit, okay. But the thing is, this cell, the current cell, must also contribute to the long-term memory, means whatever it has learned must be contributed to the long-term memory. So for that, again, if we talk about this Ig, this is the sigmoid function. So you may say these two are same. Yes, these are same, but they are having different weight vector. They are learning differently and they are controlling something different. Here, what we are having actually is, we are having one TAND activation function that will take the input value, okay, your hidden state information, the previous hidden state information, and from there it will compute some value. That value is going to be multiplied and then it will be forwarded to the summation. Means it is something like this: input gate, the tan, the sigmoid. This is the tan activation function. This is the sigmoid. Both of them is getting the xt as input and ht minus 1 as input. Okay. This will basically control the fraction of information that will be contributed to the long term. This has controlled the amount of information to keep from the long term memory. Now to that, whatever we have preserved, how much information we should add for the current RNA unit. So that is what we are going to do next. So it will give us, so tan function will give us value from minus 1 to 1. So this is we have. Now this value is going to be multiplied and then it will be contributed to this sigma. Now, can anybody explain what this for input gate is doing? So this is the input gate. Anybody? Yes, it was 50%. Yes, half of the information is written. Exactly. And you may also observe one kind of basically discrepancy is here. Even though we are saying this is a forget gate, but it is saying how much information we are preserving from the long short-term memory to be forwarded to the next, okay, or be preserved. Now, this input gate is controlling how much information to be added to the long-term memory from the current state. Means whatever it has computed, how much information from this state to be contributed to this long-term memory. I hope it is clear. Can anyone summarize it in one line? Yes, it is taking the current state as well as it is contributing to the long-term memory. So we can say this information is potential So basically we can say that this is the amount of information or knowledge the current state has generated. Now all of the knowledge, I think more, if we pass all of the information again, it will get overloaded, the long-term memory. So how much information we want to add from this potential one to the long-term memory is basically decided by which one? That input gate. Okay, so this one is your the process for what? Selective. What? Selective? Yes, exactly. Yes, Preeti. So what it is, so we have talked about the forget. Now what this is? Selective read or write. What it is? Can anybody tell? Very good. Yes, exactly. So because we are contributing the current state information to the long-term memory, so we are writing the information through this input gate. So this is, as a whole, we call it as writing, selective write process. So we had three things. Read. Okay. It is now, if you remember that we were considering the state information from previous state, so definitely we also need some state information from this RNA unit to go out. Yes or no? All agree? some information, the short-term memory should also go out. This is the long-term memory after making the contribution from the current RNA unit. Now, the question is, what will be the output that HT from this one, or HT plus one, we can, or HT, sorry, will be HT. Actually, we are taking XT, so definitely it will be the HT. So the next will be how much information, the short-term memory that we are going to flow to the next RNA unit, that is to this RNA unit. This is second RNA unit, we can say. Okay. So now I'm just expanding this one. Okay. So this was something, the output gate. So this is the XT. Now we are going to contribute from the information that we have computed. If you can recall from the previous slide, this was the information that we have computed for the current state. So I'm just writing the same thing here. I'm writing 10. Okay, the input is same. Okay. Now this short-term memory, we need this short-term memory to be created from here. Okay, we are talking about the selective read. So anyway, so now we have that final CT computed, if you can recall from here, isn't it? So this we have computed here. Okay, now the next gate that we are having is the output gate. So in the output gate, what we are going to do is, this final input will come to this stand, means the long-term memory till this current time. Okay, and then whatever TAN will give us. Okay, so so basically this was the input. This was the input, and then we are trying to combine the information from this TAN, and so what this CT is? The CT is the long-term memory after getting contribution from current state. So from the current state, whatever contribution we have got, so this CT is the amount of long-term memory that we have got after updating it with the current state information. Okay, so now this information needs to be sent as a short term also. It will get propagated to the next RNA unit, as well as from this one we also need to control the amount of information that is going to be in form of short term memory. So what was the role of this sigmoid function? Again, it will control the percentage of Okay, so based on the current input and the hidden state input, so if you can recall from the example, so it was the ht minus n1 here also. So based on the current input and the previous state information, how much information should be forwarded as short term will be basically made through this one. Okay, so with this one we have now what type of gate, what type of operation we are having here. So this is the output gate. Why we say this output gate? Can anybody answer why we say this is output gate? Anyone who can answer why we say this as output gate? Any answer from your side? Because this is the controlling, this gate is controlling the amount of information will be basically be output from this unit as an input to the next one, and this is where we write this operation is selective read, means the next unit, how much information or what information the next RNN unit will read depends on this operation only. So this is what we say the selective write. So I hope till now these three operations are clear. Any doubt till now? If you have doubt, just ask me, or I may. Okay, thank you. So I may combine this one in a single frame. So let's combine this one and write it properly. So So I hope this diagram is clear. Just look at the diagram and tell me if you are having any doubt in this one. So this was the long-term memory that was coming from previous states, the updated one, and what this is? Okay. What this is? So can you just tell me if it is clear or not? Okay. Now if we summarize this one, so the W will be W1, W2, W3, and W4. U will be U1, U2, U3, U4, and similarly, so the and this W and U is now going to be shared across the output. Okay. So if you are having any doubt in this one, you can just let me know, or else we may just move on to the next one. Yes, exactly. This W1. So basically, what will happen in forward pass? We are going through this one, okay. And whenever we are doing the backward pass, just look at the information we are having. The long-term information won't get dissipated, while the locally the gradient descent will update these weight vectors. Okay. So yes, it is learned by the gradient descent. Okay, and that too named as back propagation through time, because we are talking in terms of time units or ordering, we can say. Okay, so this diagram is clear. This is the forget gate. Even though it says that how much information we should preserve, the name is basically a reverse. Okay, this whole is what it is doing. It is selective, right? And what about this one? Selective, and this whole is basically this whole is just one RNA unit that we have talked earlier. This is the RNA unit. This RNA unit we have just expanded here. So anything else? Any doubt from this one? I think the LSTM is clear here. Now, so if I tell you one thing, that So this is the structure that we are having. These are the t minus 1, ht plus 1, and so on. So whatever. Now suppose this is ht minus 2 was coming, this xt minus 1, and then we had one long-term memory, okay, that had basically contributed to this one, okay, and this also contributed to what we are going to forward next, okay. Now if I ask you about the bidirectional LSTM, so this is in one direction only, and the back propagation, this is the forward pass we are having, and the gradient will be back propagated through time, okay. Now if I ask you, would you suggest me what the bidirectional LSTM will look like? Suppose I have one example, okay. Suppose so basically this is the value that we want to figure out. Suppose this is one example, okay. I know many of you don't like lectures, long lectures to be seated, isn't it? So can you tell me how this RNN will this LSTM will handle? Because if I give you I, then it will try to predict the next word, okay. So but the next word not only depends on this I, but also depends on the future word, isn't it? So how will this LSTM will handle this one? So what we are going to do is, we are having the two level of hidden state, okay. So the one will be in forward direction and the other one will be in backward direction. So it will start from, one will start at time t equals to suppose 0 or 1, and the other will start at time suppose t equals to t itself, okay. And then the input will be something like this, the same way, okay. That input will be contributed to this one, it will be added like this way, okay. And everything will remain same, just we are adding one more layer of that LSTM, okay. So this is the forward pass and the another one is backward pass. So it will learn the value, the next word prediction in both the direction, okay. So if we are having some scenario like this one, definitely we must go through some bidirectional LSTM. So bidirectional LSTM will definitely help us here, okay. Any doubt, sir? This has some relation. Next value generation. Yes, yes. So basically, what the next word will be there, that is what it is going to predict. Even in simple LSTM, it is going to predict what next word will be. But in this case, if we go on using the unidirectional LSTM, the context of this one will be limited to the previous word only. But we need the context of this one to be learned from the past value also. So to make it faster and accurate, we may add some one additional layer that will basically learn from this one. So one layer means one LSTM. Suppose this is LSTM 2, and from this side we are having LSTM 1. So it will learn from this side, and the another one will learn from this side. Okay. Niti, clear? So I hope this LSTM is the concept of LSTM and how we have applied this LSTM and what are the different operations in LSTM. So it's clear to all of you, okay? But still, we are left with the GRU. So let me just briefly tell you this. In case of GRU, what we are doing is, GRU is just the LSTM only, but what we are going to do is, the first thing is combine the FOR gate and input gate. Second, merge the cell state and so basically, if you look in this example, you can see a lot more redundancies here, isn't it? So this even though they look same or similar, they are being separated and they are only differing based on the weight vectors. Okay, so the authors, the same author along with some other colleagues have proposed the another gated recurrent unit that basically combined this input and forget gate, and the other changes was made like just merge these two values, means rather than treating them separately, now we will basically merge this CT minus 1 with HT minus 1. Okay, sorry. Okay, so in the next hands-on, we will just see the architectural diagram of GRU, and it will be very clear to you what this GRU mean and what changes has been made. So if it is clear, this LSTM is clear, definitely the GRU is nothing, just merging of the forget and input gate and merging of combining and merging of these two concepts. Okay, so I hope this LSTM and the basic of GRU, what the changes have been made to GRU is clear. Any doubt till now? Okay, thank you, man. So anyone else who is having some doubt may ask, or we may wrap up for this session. We will meet in the second half, starting from 5. We will have some hands-on there. Okay, we will see some programming on this one. Any question? Anyone? Any doubt from this one? Input, forget gate, the input gate. So the gate is this one, isn't it? The gates are this one, 2 and 3. This combinedly operation is selective write. This combinedly operation is selective read. Okay, in the selective read, this output gate is basically helping you. In selective write, this input gate is helping us, and what information to preserve from the long-term memory for this current state will be controlled by this forget state. So forget gate, sorry. So sir, basically it is all about the weight that we are using. It is not about attention, but just look at here. We are basically sharing these weights. Okay, this is the 1 unit. Okay, and this is the weight vector that we are learning. So in the next unit, let me just write it here. In the next unit, so suppose this is the 1 unit, unit 1. This is the second unit. Here we are learning the weight matrix W and U. Here also we are learning W and U only. Okay, this weight matrices will be shared across the unrolled hidden states. Okay, so if they are remain same, the context they are basically the context on which they are being updated using the gradient descent will be preserved by these weight matrices. If they would have been different, definitely that context would have been missing from the learning. But as we are sharing the same weight vector across the input lane, so all the information that it has already seen, this weight has already seen, definitely will be preserved by this weight vector only. Okay, so this is how it is working. Here we are not concerned about the attention, but the way we are basically applying the weight vector, the weight matrix across the unrolled layers. Getting my point, Pradeep sir? Anyone else, if you have any question or any query, or if you want to suggest anything in this one? So I think now you are clear about the LSTM, at least the concept of LSTM. The motive I think already discussed. We all know the motive. The LSTM, the purpose of the LSTM was simply to control the information the way it was flowing in the RNN. Okay, so that we can minimize the problem of vanishing gradient descent as well as exploding gradient. Okay, while preserving the long-term dependency. But when it comes to the long-term dependency, we are preserving only the amount of information that is important, and that is basically being done by the gates only. So I hope it is clear to all of you. Okay, so no more questions. So let us, thank you so much, sir. We will meet in the second half, and we will have some hands-on along with the preliminary discussion on the GRE. It is just 5 to 10 minutes it will take, as the session was delayed due to the previous session. So sorry for the delayed session, and hope you have enjoyed the session. Thank you so much. We will meet at 5 in the next session. Okay, thank you all. Thank you all, Astos.
Okay, sir.
Okay, thank you.